Hello, grade 12s and colleagues and friends. And today we're going to handle this little piece. And what is so special about it, you know why. You know why. Okay? So obviously, guys, a little bit of carefulness in our thought and approaches needs to be on point. Otherwise, I will take this opportunity to thank you guys for supporting my channel throughout, and essentially I can see the effects or the shockwave effects of this bullet shots that I give here. So I do hope that this impacts on you positively, and certainly will do so for even the few groups of students to come even after you going forward. Otherwise, this is probably one of the last videos I will be posting in this channel, and for a very long time you may not see me do any activity whatsoever. But seeing that most of the knowledge contained in this paper is as old as 20 years ago and even beyond that time, to see it being examined consistently today is amazing. So this is to suggest that this channel may still be relevant even 5 years going forward. Anyway, guys, so let's not talk too much. So this was a special paper and you can see why. All right, so general instructions, nothing really special. Then local instructions to question 1. Basically, they highlight that there's only one correct answer. But remember, these kinds of questions, or rather instructions, they can be suggesting that there is a time when an examiner may just provide 2 correct answers deliberately, just to check if a student adheres to instructions. Choose only one answer. Even if there's 2, choose whichever you like, but usually be very careful. There's sometimes a catch on the other one. Okay. So not a big deal, guys. So let's just go for it and handle it nicely. Now we are told here, or we are asked, which one of the following industrial processes? So we studied industrial processes because, we didn't just study chemistry for fun. It has some industrial value or direct applications to what improves our lives. Okay, now which one of those processes is used to prepare sulfuric acid? Okay, so this was in the section of inorganic chemistry. All right, so let's see. We know that usually it involves a few steps: burning sulfur in air to form sulfur dioxide gas. All right, and this sulfur dioxide gas, we basically react it with oxygen as well. So this is the catalytic oxidation. So using the catalyst vanadium pentoxide. Okay, so, and this was called the contact catalyst. So this is a catalytic oxidation of sulfur dioxide gas. This produced sulfur trioxide gas, which, because we know this sulfur trioxide gas is soluble in water, it can react with water to form our desired friend, which is H2SO4. This was the process. And now what was the defining part of this process is this use of this vanadium pentoxide, which was called the contact catalyst. Okay, and as a result the process was termed a contact process. Okay, this is very important, and we know that essentially sulfur dioxide gas is itself highly soluble in water. If we let water come into contact with this one, what happens? We form sulfurous acid. This is an acid of intermediate strength, meaning it's neither a strong acid nor a weak acid. It's in between. And this was proved by the fountain experiment, because with this we used an experiment called fountain experiment. Okay guys, I'm just giving you a lot of information at the moment because I'm just trying to teach you at the same time. Although I'm not going to teach you like you would be taught in class, but I'm just going to try and give you some things. Now with the fountain experiment, we saw that this gas, when trapped into a syringe and then we connect with some tube or an straw into water, this gas actually would suck in the water, and the litmus paper would change to show that it's an acidic solution that we get as a result. So very important stuff to know. Of course, this is the first step where we produce sulfur dioxide, and when we react sulfur dioxide with oxygen, that would be the second step using the contact enzyme, and then water and sulfur dioxide gas would be the third step and the final step, which yields our sulfuric acid. So obviously guys, you would know that the Haber process is the industrial process for the production of ammonia. Ostwald process is the industrial process for the production of nitric acid, and then this one is used in the chlor-alkali industry. And basically the main products here is hydrogen gas, chlorine gas, and sodium hydroxide. Okay, very useful products, by the way. So essentially guys, it helps to understand these things nicely. And one thing that one needs to note, overall, all of these, maybe let me write it this way, all of these, including this electrolysis of brine, these are somewhat redox reactions, or let's just say redox reactions are involved, because some reactions in this chain of reactions are essentially redox reactions, but others are ionic exchange reactions, others are acid-base reactions, and so forth. So it helps again guys to know this literally. In fact, if you noticed throughout the years, you'll notice that most of the questions in the MCQs are just previews of questions coming in the long questions. So if you miss it here, you are more likely to fluff it in the next one, unless you wake up along the way and then it reminds you of what's going on. So this is more of a reminder, or something that gives a second chance to shape up a bit if you're getting a bit messed with. So it's very important to stay awake and stay alert here. Like I said, for me, MCQs should be answered first. Why? Because they give you a preview of the rest of the paper, and therefore you approach those questions with a little bit more comfortability in you. But otherwise, remember, don't fixate on that though. Know it, but don't fixate on it, because it can backfire. All right, next question says, which one of the reactions below is the best explanation why nitrate compounds are used in the manufacture of fireworks? Remember, these ones involve combustion, so this is because of the anchor that there is a release of large amounts of oxygen gas. So literally the use of nitrates in the manufacture of fireworks is because of the release of large amounts of oxygen when we burn these. Okay, so let's have a look. Obviously this is already eye-catching. It's suggesting that that should be the answer, because this is the only one that releases oxygen. Okay, obviously guys, in the lab we used nitric acid. We just burned nitric acid, and what would happen when we burn it? We would see that obviously we produce nitrogen dioxide gas plus oxygen. All right, and these are just, with these equations, sometimes it's not easy to remember them, but what is easy is what are the products. Obviously you can see that there's hydrogen and some other oxygens here, so most likely there's going to be water. But the third one, if you can get the two main products, the third one is easy to make up by just knowing how chemical equations work. But now this is not balanced, so we can try a 2. Remember, when we balance, you test from 2, because we can't use 1 for sure. We use 3, we use 4, we use 5. Usually you will come to an answer here, but don't limit yourself to this. So try odd. If it doesn't work, try even. If it doesn't work, alternate and increasing order. You will get your answer. So if we use a 2 here, hydrogens are 2. There's 2. It looks all right. Nitrogens are 2. There's 1, so we can put a 2 there. And then oxygens are 6. And then here we've got 4 plus 2, that's 6, plus 1, that's 7. So this already says it's not working. So this can be trial and error, folks. So if a 2 doesn't work, the next step is to try a 3. If we put a 3 here, we're going to have 3 nitrogens. This is going to force us to have 3 nitrogens. Then there's 3 hydrogens here. But now do you see we've got 2? So an odd number doesn't work already automatically. So let's use a 4. So if we put a 4 here, we're going to be forced to put a 4 there. Now we're going to be forced to put a 2 there. Okay, maybe let's sort this out nicely. So we're going to put a 2 there. So there's 4 hydrogens, 4 hydrogens, 4 nitrogens, 4 nitrogens. Then there's 12 oxygens. There's 8 oxygens plus 2, that's 10, plus another 2, that's 12. So this is a balanced chemical equation. So now balancing was not necessarily an issue, but an issue was forming the reaction itself, because it became very important to know what's going on in here. So obviously this one, we notice it by the brown vapors that form. But how do we know the oxygen? We know the oxygen is produced by using what we called a glowing splinter that does what? That ignites. Okay, so essentially you take just a glowing splinter, you just light it and then you switch it off while it's still glowing. You put it closer here and then it ignites. Boom, it bursts into a fire as well. So this was the experiment we performed. We used this one in the school lab, but you can see that you can also burn a nitrate. So in this case, potassium nitrate, which produces potassium nitrite. This is going to give us essentially whitish vapors, and if we put our glowing splinter in there, it ignites. It bursts into a fire because of the oxygen release. So this is very important. Again, these questions, they depend on whether you know or you don't. But I often looked at these questions even in more detail to understand what's going on. I found a lot of great understanding in these, because knowing also the type of reaction that is going on here is important. But let's just leave that for now to whatever we're going to come across. But know how to form equations by just knowing the products and the reactants, mainly. And then the balancing is a game of numbers, so you play with the numbers. All right, great. So if we look at this one, sodium nitrate and sulfuric acid, we form nitric acid, and sodium sulfate. Can you see there's no oxygen being released here, and neither is there oxygen being released here. But of special note is that this reaction in particular, we used that reaction in the lab to produce nitrogen dioxide gas, which is a brown vapor that we see here. And then we played with it, by pressurizing it and stuff, and then it changes into dinitrogen tetroxide and all that. So very, very, very interesting stuff. But let's not say too much at this moment. We just want to keep the time while we learn as much as we can. And obviously this is just the decomposition of potassium nitrate into its respective ions, but there's no release of oxygen there. Now 1.3 says copper sulfate and iodine crystals. So what do you know about this one? Copper sulfate is an ionic substance, and that means it's polar. And iodine crystals, this is a molecular and it's essentially non-polar. Okay, I added to a test tube containing water. Now we can see water is a polar solvent, as well as tetrachloromethane. Now this is an organic substance or solvent that is non-polar. So most likely this is a question on solubility. And under the principle that says likes or like dissolves like. Okay, so this was a very common question in chemistry from grade 10 through grade 12 essentially. Now let's have a look at this. Now we are told here the test tube is thoroughly shaken. After allowing the test tube to stand for some time, the contents separate into two layers with the aqueous layer on top. Okay, so let's just picture this. What is going on here? So we've got this container and it separates into these two layers. The top is H2O and the bottom is tetrachloromethane. CCl4. Again, it's very important to know how to write these. So this is carbon tetrachloride. Okay, obviously in this layer in between, water is going to be partially soluble, as well as that one is going to be partially soluble, but the bulk of these don't really mix nicely. Okay, now why is this one at the bottom? It's because of density. Tetrachloromethane is more denser than water. If you look at the molecular weight of water, it's less than the molecular weight of tetrachloromethane. That's interesting, is it not? It definitely is. Okay, good. So now we bring in an ionic, so we know that copper sulfate is going to dissolve here. Okay, and we know that the iodine crystals are going to dissolve here. Okay, because like dissolves like. And obviously what's the color of copper sulfate? Because of Cu2 plus ions, they will impart a blue color. And iodine in tetrachloromethane is going to impart a purple color. But obviously, guys, this purple color is not exactly purple. Technically speaking, this is violet. It's only purple in trichloromethane, which is chloroform. But again, purple and violet has been fairly confused in many texts, so at times the separation sounded like it's not very clear, but we know there's a very clear difference between these two colors. But anyway, we can accept purple, all right, so not a big deal, guys. Let's move on. Which one of the sets of observations and corresponding reasons. See, corresponding reasons from an observation in the table is correct. Now the bottom layer turns blue. The answer is a definite no. Why? Because we know copper sulfate dissolves in water, so it will be in the aqueous layer. Is it because copper sulfate dissolves in... No, it does not. And then we know the top layer turns blue. Yes, because copper sulfate dissolves in water. True. Now already that's our answer. The bottom layer turns purple. Remember, what is obvious is not always the answer. Be very careful. The bottom layer turns purple. Well, it's arguable. We can say violet or purple. It's okay. Is it because the I2 is more dense? It's not a question of density, but of solubility. Okay, so this is not correct. But this can be confusing. One can make a mistake because truly this is more heavier than the copper sulfate, without a doubt. Okay, the top layer turns purple. Definitely no. And it's definitely not highly soluble. It's not highly, but partially. Okay, we need to understand these things, guys, because remember, you will become a doctor and you'll have to make a clinical decision. Someone comes with a headache, and this headache is involving the face, especially around the eyes and the malar regions of the face. And that's already suggesting sinusitis, okay? So that is your immediate thought when someone describes a headache like that. And even on the temples, because the sphenoid sinuses are deep in there. So usually the pain from there kind of radiates into the sides like that. Now, a doctor could say sinusitis, gives antibiotics. That's a problem. How do you treat something you have not understood? That's why the doctor's approach works. Now you have to ask a few questions and be like, okay, when was this headache of yours, or when did it start? They will tell you, it started, 2 days ago. Okay, fine, that looks recent. Now, a history of trauma of 6 months ago may not be relevant, or even a year ago. So again, you need to know what is relevant in the story, because some people just take information carelessly. You need to select the right information. So we know that this is a recent occurrence and this is a sinusitis. But the question is, what is the most likely cause of the sinusitis? Now you can ask, did you have a flu-like symptom recently? Were you coughing or things like that? Then if they confirm yes, you know that this is most likely infective. So this would need antibiotics. So now they become appropriate. But if someone says he was working in a place where there was a lot of dust, you know that this could be irritation from particulate matter that set in the sinuses. And so this one is not infective in origin. All you need is just anti-inflammatories, and that's it. But if then there's dust particles or any particulate matter that is possible, you may need to refer this person to an ENT doctor, the one now who specializes in the nose, ears, and the throat. We call them otorhinolaryngologists. So they can go and clean that using their special instruments called scopes, or they can syringe the dust particles out, so that this doesn't continue to become a chronic inflammation. So you see, the appropriate treatment is taken from the right understanding of the problem. Otherwise, if you don't get it right, it sounds right. You see, this one sounds right. But now if you understand exactly what is going on, the observation and its corresponding reason, now you start to realize, density is not real. Density is basically for the separation of the two layers rather than the color change. You understand that? So that's the idea. So again, guys, this is very important. I'm just trying to emphasize the fact that certain things are very important. And someone may say, no, I had made a fire and there was a lot of smoke, or maybe a building burned and stuff like that. Then you know this is just chemical inflammation. So it was due to irritation. So only anti-inflammatories and no need to refer to anyone else. Of course, you give warnings. Come back if there's a problem, so that if you missed it, you can then sort it out quickly. So I'm trying to emphasize, guys, the fact that the doctor's approach works here also. You need to understand the question so that you can pick the right combination of answers to solve the problem. So don't be a careless individual. Okay, let's not spend too much time there. So we are done. Next question says 5 grams of each of these gases. So we've got we've got carbon monoxide, nitrogen dioxide, ammonia, and sulfur dioxide gases are sealed in separate containers. Now the temperature of the gas is the same. Now, meaning we are keeping it constant in each container and it remains constant. Okay, fine. I don't know what this is trying to say, but we can just say the temperature is the same for each. I think that would be best. In fact, it means so. And it remains constant. Okay, meaning we're not changing it. So already, guys, this is suggesting something, some relationship. Now the graphs show the relationship between pressure. So the relationship between pressure P and the reciprocal of volume. Now the reciprocal of volume is 1 over V. Okay, great. Now for each of the gases. Now this gives the vibes of PV, the general gas equation, is equal to nRT. Now remember, we have kept something constant. So if we kept something constant, this is T and R. But now we want to explore the relationship between these two. So if we divide by by V, this is going to be P equals nRT over V. And if we simplify this further, we're going to see that P is equal to nRT into 1 over V. Okay, and now what do we notice, guys? This is a constant. So this is a constant. Okay, now what does this give us an idea of? Remember, these are straight lines, are they not? So an equation of a straight line is given by y equals mx plus c. But seeing that this passes through the origin, all of the straight lines pass through the origin, we know that c is 0, implying that y is equal to just mx. And we know that m is a constant. That's the gradient. And this would also be the gradient in each of these graphs. So this becomes the gradient where 1 over v can change, increase or decrease. So essentially, guys, it helps to note the equation that explains any graph that is given to you so that you can make a justifiable decision and most appropriate choices be selected. But now, guys, we're using 5 grams of each gas. But we notice that there's different gradients here. So what is responsible for that? We can see that 5 grams of each, but their molar masses are different. So this means the number of moles here is the culprit. Because the same mass will be different in terms of number of moles because of their molar masses. So obviously this is suggesting that the greater will be the greater is the number of moles here. The greater will be the gradient here because temperature is the same. The general gas constant is the same. So what will be different for each of these gases will literally be the number of moles. Now we go back and say, okay, number of moles is calculated as mass over molar mass. But now, do we really want to calculate the molar masses? The answer is not necessarily. But what we need to do is to know that with ratios that have the common denominator, the common numerator, let's just do this. So what do you see, guys? This is 0,5. This is 0,25. This is 0,1. Can you see? So we notice something, that if we increase the denominator while keeping the numerator the same, the ratio decreases. So this is already suggesting that the one with the greatest molar mass will have the least number of moles, and the one with the smallest molar mass will have the most number of moles in this case, which can explain these. So if we look at carbon monoxide, this is 12 plus oxygen. So 12 plus oxygen will give us 28, because this is 16 plus 12. So this is 28 grams per mole. Now nitrogen dioxide is 14 plus 16 times 2, that's 32. This gives us a 46. Is it 46 or 48? Wait, 14 plus 16. No, plus 32. Yeah, that's 46. And then ammonia here, it's 14 plus 3, that's 17. This is 32 plus 32, that's 64. So we can clearly see here that the one with the smallest molar mass is ammonia. And if it has a smaller molar mass, for the same numerator of 5 grams, calculating the number of moles will yield the greatest ratio there. So this is the one. So this one should be for ammonia. And the next one, that's 28. That should be carbon monoxide. And the next one is going to be 46. That would be nitrogen dioxide gas. And then the last one is going to be with the greatest molar mass, which is sulfur dioxide gas. So it is very important to try and understand what you're given, guys, and of course using the right principles. At some point, you just use models if you can, so that you don't struggle too much to make sense of a simple situation. I don't know, this thing just rotated now, and my intention was to just reduce the size, that's all. All right, so now any student would like to just calculate this directly. It's not a big deal. You'd still get to the same answer, but that would be wasting time. So use a bit of logic to get to the answers much faster. So now we understand. The question says now, which graph will represent the correct relationship of P and 1 over V for ammonia gas? This is K. So this one, as you can see, we had to work it out a bit by trying to integrate topics and essentially use a bit of logic to answer without really doing too much. And you can see, guys, here, this is a direct proportionality. So we can easily see that pressure is directly proportional to 1 over V. Because as 1 over V increases, and so will the pressure. But let's just double check here. Sometimes this, okay, that is pressure. Because these units go missing because of these old text boxes that don't correlate with the new gadgets. So this is in kilopascals. Okay, so this is great. So we know that this is pressure in kilopascals, and that's very important. So we'll appreciate that as pressure increases, the 1 over V increases, or vice versa. So this is a direct proportionality. A straight line that passes through the origin. But pressure against volume is a different story, because volume is in the denominator. So this would mean an indirect proportionality between pressure and volume. But pressure and the reciprocal of the volume, it's a direct proportionality. So that's something to appreciate, guys. All right, so let's move on to the next question. So I hope we answered that question fully. So the others are not important anymore. All right, okay, all right. So let's look at this one. Jason bubbles hydrogen sulfide gas. Now this gas, hydrogen sulfide, was described, we produced this one in the lab. So this is described as the rotten egg smelling, or we can say it has a rotten egg smell, or we called it sometimes a pungent smell. Okay, so yeah, that's the story. And in fact, sulfur is usually something that smells bad when it's rotten. So it's because of the sulfur in there. And of course, we've got sulfur dioxide gas here. Now, what do we know about sulfur dioxide gas? We know that this one has a choking smell. I don't know if I'm writing choking properly. I think I'm not writing it properly. So this is, it has a choking smell. And a choking smell is basically chlorine-like. So I'm just trying, guys, to give you as much as I can. Respectively, these gases are bubbled through acidified solutions of potassium dichromate in separate test tubes. Now the question is, why do we acidify? Well, first, we could do this because we want to achieve some electrical neutrality of the solutions. Or the second reason could be, if we get a precipitate here, we want to kind of dissolve that to get a fine solution. So this would be to dissolve the precipitate. So that could explain this. So sometimes it can be asked, why do we acidify? This could be for electrical neutrality or to try and deal with the precipitate that can form and perhaps mess up with our results. So we just want a nice solution there so that we can look at the observations we're probably looking for. Very interesting stuff, hey? So guys, here you're going to be learning chemistry now, not something like chemistry. All right, guys, so again, this is a section in inorganic chemistry. But now if we look at this, potassium dichromate, the dichromate ion is a very strong oxidizing agent. The dichromate ion itself is a strong oxidizing agent. The potassium is just playing a spectator role here. So the dichromate ion is a strong oxidizing agent. Obviously, these ones are fairly strong reducing agents when acting with a strong oxidizing agent, but they themselves are weak reducing agents in general. Okay, so we can already see here that we are dealing with the redox reaction. And what's the color of the dichromate ions? It's orange. So we know that this has an orange color. This is very important. Again, if you haven't done the experiments, you will not remember this. Okay, guys, I think I'm taking too long. So this is orange in color. Great. So now we are bubbling these gases through. So that means we're going to get redox reactions here. Because if we have a strong oxidizing agent, these should be functioning as reducing agents. Okay, so now, what is the story? It says, which one of the following statements with regard to the above experiment is correct? Now, the solution of test tube X changes color because the dichromate ions are oxidized. The question is, are they truly oxidized to chromium ions? The answer is, if this is an oxidizing agent, it undergoes reduction. So they are actually reduced, not oxidized. Okay, so as a result, this is not correct. Both test tubes, the gases are oxidized to this. Now here we need the standard electrode potentials, otherwise we'll be in trouble. All right, guys, so we've got our standard reduction potentials. Remember, guys, don't guess too much. Sometimes the hunch would be like, perhaps, but be very careful. Certain things need you to test them out to confirm. Now let's see, where is sulfur dioxide? And remember, guys, for reducing agents, it's always the first substance listed on the right hand side. Those are the reducing agents, not the added stuff. What is added is not what you consider as the reducing agent. This is just for balancing stuff, for electrical neutrality of some sort. So if we look at sulfur dioxide gas, there it is. Now sulfur dioxide gas is over there. Maybe let's use another color here to highlight it better. Now sulfur dioxide gets oxidized to the sulfate ion, because remember, oxidation is going to be in that direction, whereas reduction is going to be in that direction. But now with the dichromate ion, which is over there, we know that this is a stronger oxidizing agent. It gets reduced. Now these ones will be oxidized. There is hydrogen sulfide. Okay, again, hydrogen sulfide is going to go in that direction as well, because it's going to be, now can you see this one, sulfur dioxide gas is oxidized to the sulfate ion, but hydrogen sulfide is oxidized to sulfur. This would be a precipitate. Okay, maybe let me write it nicely. This would form a precipitate. Okay, now remember, if we're having a precipitate, it's going to cause some issues with our observations. So we want to acidify this thing so that we can just see a fine, clear solution of the precipitate, mainly on the walls of the container, but so that we can observe the color changes of the dichromate ion nicely. Can you see? So this serves two purposes here, to deal with the precipitate and also for electrical neutrality. So the answer is no, not both, but only the sulfur dioxide gas. Now in one test tube a precipitate is formed. This is true. Can you see how the standard reduction potentials help? They help a lot. Now hydrogen sulfide acts as a reducing agent. That's true. Where sulfur dioxide acts as an oxidizing agent, that's not true. As a result, that statement is wrong, because they both act as reducing agents. So definitely our best answer here is option C. So guys, it helps to know these things. And as you can see, guys, this becomes a reducing agent and a reducing agent. Okay. Now, can you see that even though this was inorganic chemistry, we are applying redox reactions, and the standard electrode potentials sometimes feature and they assist in answering adequately. So I hope you guys can follow the drift. Next question says, each of the two reactions X and Y below are respectively in equilibrium in two separate sealed containers. Sealed means closed system. So understand the language. The English used here is technical, or it's strategic, so it has a meaning. Now reaction X is hydrogen iodide gas decomposing to hydrogen gas and iodide gas. Okay, great. And reaction Y is the decomposition of calcium carbonate into calcium oxide and carbon dioxide gas. Okay, now the pressure in both containers is now increased. What? Pressure is increased by decreasing the volume. Okay, not a problem. So now this is an application of Le Chatelier's principle. What affects the chemical equilibrium? It's pressure, it's temperature, and amount of either products or reactants. Now let's have a look here. We will see that here there's one gas molecule of iodine gas, one gas molecule of hydrogen gas, together making up 2 over against 2. So we know that increasing pressure here will have no effect, because the number of moles on either side of the equation are equal. But here there's one gas molecule of carbon dioxide gas and nothing else. So this would mean if we increase pressure here, we will decrease, we'll favor the reverse reaction, because it has the least number of moles according to Le Chatelier. So obviously here, what is going to happen here, we will favor the reverse reaction. Okay, great. Not a problem. So now it says, how will the number of moles, meaning the amount, of the products. Can you see? Specifically products. And now remember, for any chemical equation, whether reversible or not, what is on the right are the products, and what is on the left are the reactants, and that's it, unless otherwise stated. So these ones up here on the right hand side of any chemical equation, unless otherwise stated. Now, what do I mean about this? Remember, in a reversible reaction, if we're focusing on the reverse reaction, then what was reactants become products. But under normal conditions, when a reaction is given like this, it's always given in the forward direction, and the products are always on the right, where the reactants are on the left. So again, be very careful here of how to deal with this. And we always read our equation from left to right. That's how we read our chemical equation. Now, let's have a look here, guys. We are told here, how will the number of moles, or in fact, we are asked, how will the number of moles of the products in each reaction change? Obviously, for reaction X, there will be no change. Anything that says otherwise is already eliminating those options. But what about in Y? We know that these products are going to be converted back to reactants, so the products will decrease. So we know that this is true. They will not increase, they will decrease. They definitely are not going to stay the same. So the one that ticks all the boxes is option C. So what did we do here? We applied Le Chatelier's principle, nothing else. Okay, now let's move on to the next question. Methanol, which is CH3OH, can be manufactured from carbon monoxide and hydrogen gas, as indicated by the following reversible equation. So when the equation is reversible, what is suggesting, guys? It means it can achieve equilibrium. All right, because for any equation or chemical equation to ever achieve equilibrium, it has to be reversible first, but another statement needs to come in as well. Let's read on. Now the graph below shows how the concentration of methanol changes with time when carbon dioxide and hydrogen gas are mixed in a closed container. Wow, there is the word we were looking for. Now, closed container means closed system. Now, once you combine the closed system as well as a reversible chemical reaction, we are definitely talking about chemical equilibrium. In fact, the word dynamic would be even better. Dynamic equilibrium. So remember that. Okay, so analyze the statement, guys, like you would analyze a story from a patient if you become a doctor one day. If you want to be good, you will start practicing this now with chemistry, because these skills, guys, they grow into something meaningful in the future. But no one is going to teach you these things per se. They will tell you the principles, but you'll have to apply them. Right. Sometimes you've got to bend those rules a little bit. Okay, we see here, we can't read that thing. This square brackets, this is basically concentration. So, I mean, these are old little text boxes here, so they sometimes don't read so well. So this is CH3OH, concentration, and this is how it changes with time. Okay. Now, this is in the presence of a suitable catalyst. Can you see? This one is not really significant per se, or maybe we don't know. But this is some information which probably doesn't matter, because here this is just saying we can achieve this much faster than we would if we let this happen, maybe spontaneously. If the forward reaction is exothermic, we don't know. Okay, so the question says, let's look at the graph. Remember, analyze all pieces of information before delving into the questions. Now we see the graph here. We see that the concentration starts from 0, increases, okay? And obviously, methanol is the product, so this is essentially the forward reaction because we're producing more and more. So the concentration increases, and then stays the same. From here, it literally plateaus. And what happens when it plateaus? Remember, this is a closed system. And that is a reversible reaction. So the question is, will we ever run out of our reactants? The answer is a hell no. Because in a closed system, as soon as this forms, the reverse reaction kickstarts to achieve a dynamic equilibrium. So this means this is the state of dynamic equilibrium. Okay, great. And remember, the state of dynamic equilibrium is not equality, but it's a constant state. So the concentrations of substances are constant, and we can see this is constant. So please, it does not mean these are equal, but it just means they don't change, or if they change very little, so that there's not, in fact, it's almost as if there's no change at all. So again, a question like this can throw you off if you don't listen carefully to what is given and you don't analyze properly. Now let's answer the question. Which one of the following best explains why the graph becomes horizontal? The forward reaction has stopped. This is a catching statement. It would be easy to say that, because if you didn't pay attention to the fact that this is reversible in a closed system, you would say that. But in this setup, the reactions never stop. Dynamic equilibrium just means the forward reaction, the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, RFR is equal to triple R. So that's the story. So they never stop. They continue, but at equal rates such that the changes are not noticeable or insignificant to note. So the answer is a definite no. There is no carbon monoxide left. We never run out of our reactants in a dynamic equilibrium, because as soon as we form products, we convert those back. So the answer is a hell no. The rate of the forward reaction is equal to the rate of the reverse reaction. Definitely, our statement is 100%. Now, all the reacting gases have been converted to methanol. We never run out of our reactants. So that's not the case. So can you see this statement right here could be confusing together with statement A, but understanding the setup and the information given actually then dispels the problem. So C becomes our answer. So again, guys, this is the same thing, that if a patient presents with a similar thing, or at least a condition that can be caused by multiple other things, but we almost always assume infection. For example, our analogy of sinusitis. If you don't realize that this could even be allergic rhinitis, maybe someone was exposed to some, allergen or pollen. Maybe it's happening in August when there's wind and stuff. So there's pollen flying around. So this could easily be even allergic rhinitis. So be very careful, guys. Don't jump to one small conclusion because of the obvious nature of the questions. Pay attention to the specific question being asked and the circumstance of that question itself, so that you can find the right answer. All right, let's learn on, because I don't want to take too long saying the same thing. 1.8 says solutions X and Y in the table are mixed. Okay, now one of the combinations of X and Y produces changes, forms products that change blue litmus paper to red. Now, once we change a blue litmus paper to red, it means we produce an acidic product. Because we were told that this forms a product that changes a blue litmus paper to red, and it means we are looking for an acid product. Now we look at silver nitrate reacting with zinc chloride. This is basically an ion exchange reaction, because we can see zinc will pick up the nitrate, so we're going to form zinc nitrate, and silver will pick up the chloride and form a precipitate. So this is a whitish precipitate, which is silver chloride. And now a precipitate is insoluble. So we know that AgCl is insoluble. So if it is insoluble, it means it won't take part in making up a solution that we can test with an indicator. So that means it does not even participate. But now zinc nitrate, all nitrates are soluble in water, and essentially this is just a salt, so it will give us the pH of water of 7. So that is not going to change the blue litmus paper to red. Now sodium carbonate with barium chloride, again barium is going to pick up the carbonate and it's going to form a precipitate. Okay, barium carbonate is going to form a whitish precipitate, and this is again insoluble. All right, and that means it doesn't take part in any solution that we can test. So what remains is sodium chloride, and sodium chloride is salt, so it will give us the pH that is 7, because the pH of salt is 7, or that of water. Now sodium sulfate and barium chloride, again we're going to form barium sulfate, an insoluble stuff, because it will form a precipitate, again a whitish precipitate, and essentially sodium chloride is going to leave us with the pH of water. So once we eliminate 3, this is definitely going to be the answer. But how do we know? Hydrogen sulfide, there's going to be an exchange here. We're going to form here zinc sulfide. Now zinc sulfide is basically a yellowish white precipitate. So meaning it's going to be insoluble. Right. And therefore it won't take part in any issues of our little things. But now what also is going to happen, we will form HCl. We're going to form 2 HCl, and this one is an acid that dissociates into the hydrogen ions and the chloride ions. So we're going to have 2 of each, and because of those, the pH is going to be less than 7, and the pH less than 7 will change a blue litmus paper to red. So this is our answer. So guys, again, it helped to know these ionic reactions in a way, so that one could understand how to use these, and even the knowledge of these precipitates and why they would not cause any confusions, because if these were to be soluble, it would be another issue. Okay, be very careful of such things. Anyway, let's move on. If base X is titrated against acid Y, the pH of the solution at the end point is 8. So what does this say? It means we are using a strong base and we are reacting it with a weak acid, and then we are forming a basic salt plus water, mainly because it's an acid-base reaction. Okay, all right, okay, so this is basically suggesting that this is going to be a basic salt which will result in a pH greater than 7. So that is the story here. So very easy, hydrolysis and what. Okay, let's have a look. Sodium hydroxide is a base, so definitely it's a strong base. Any hydroxide is a strong base, okay? And ethanoic acid, definitely this is a weak acid, so already A is the answer. But remember, the most obvious may not necessarily be correct. There can be a catch in there. Be very careful. Sodium carbonate and HCl, this one is going to yield sodium chloride plus carbon dioxide and water. So essentially here, carbon dioxide is essentially acidic because when it reacts with water, because of carbon dioxide, when it reacts with water, it forms carbonic acid. And carbonic acid will dissociate into hydrogen plus the carbonate ion. All right. And these guys are responsible for a pH that is less than 7. So this one, no. The pH won't be greater than 7. Again, know these things, guys. And then sodium hydroxide, yes. But sulfuric acid, no, because this is a strong acid. This results in a pH that is exactly 7. It's a complete neutralization, unless something is in excess here. Sodium carbonate and ethanoic acid, so this is a weak base with a weak acid that results in a pH of 7. So not 70 but 7. So obviously here, guys, A is definitely unchallenged, but be very careful. Don't jump to conclusions too soon. Make sure you have made the necessary analysis to make up your mind about what is the correct answer. Now consider the graph below. So again, we need to look at what this is. Translate. This is EP. This is potential energy. Okay, so potential energy, EP. Now let's check in what units, because you see these were old things in kilojoules per mole, so this is just nothing but heat. So kilojoules per mole. Okay, so this is just heat, potential energy, and reaction coordinate. Again, guys, pay attention to units given because it can be confusing. Now we can appreciate that the reactants here, and these are products, because remember we read this in the forward direction. So the reaction starts at 0. Obviously it's going to be reactants reacting to form products. Now we can appreciate that the energy of the reactants is higher than the energy of the products. So this means we have an exothermic reaction. In fact, we can say the forward reaction is exothermic. So the forward reaction is exothermic. So what does that mean? Delta H is less than 0. So guys, these analyses or analyzes are very important. I cannot overly emphasize these. So now that we understand what's going on, let's read. Which of the following reactions can be represented by the graph? Meaning can be represented by the graph. Can be. Not necessarily represented by the graph, but it's a possibility. Obviously, this is an exothermic forward reaction. Let's have a look. Reaction X, calcium carbonate decomposing into calcium 2+ ions and the carbonate ion in a reversible fashion, but we are told delta H is positive, and this is for the forward reaction. Remember, delta H is always represented for the forward reaction unless otherwise stated. Okay, so obviously this is an endothermic forward reactions because delta H is greater than 0. This is endothermic. So obviously if we look at our graph, the forward reaction is exothermic, so this one cannot be represented by this graph, and obviously this one should, even if you didn't know. The burning of methane gas, remember hydrocarbons, we can say combustion of hydrocarbons are highly exothermic reactions because large amounts of heat are released, and that's why we use these for energy production. So obviously because they are highly exothermic, they could definitely be represented by a graph like that. So obviously the answer is reaction Y only. Okay, so when you know what's going on, guys, and you understand, obviously, if reaction X is not, reaction Y should, but it can't be both. But there is a fight. It could not be any of the two. So even if you didn't know for sure, this one could leave you hanging, because it'd be like, but why not D? Is it possible that Y only, or is it possible that none of the two? So a little bit of background knowledge is important. All right, guys, not a big deal. Okay, let's not lie, it's a big deal. If you don't know these things, you will not survive. Okay. All right, let's move on, guys. Okay, let's try to wrap this up quickly. Now, for metals T, V, Y, and Z exhibit the following properties. Only T and Y react with 1 mole of hydrogen chloride, or HCl, to form hydrogen gas. Only these ones. So what do we know anyway? We know very well that when we take a metal and then we react it with an acid, we produce a salt plus hydrogen gas. Sometimes there may be water, or depending on what we have. But the main product is salt and hydrogen gas. Great. But now the salt, it's a metal salt, right? Because if there's a metal there, the metal is going to be here. So for example, take copper plus HCl. It will form CuCl plus hydrogen gas. And obviously this one has to be 2, right? Right. Now look at this, guys. You will notice that copper is in its zero oxidative state, or oxidation state. And then here it's 2 plus, it's oxidized. And then if we look at hydrogen, it's 1 plus, but now here it's 0 because it's in its natural state. So can you see copper is being oxidized while hydrogen plus ions are being reduced. So this means we have a redox reaction. So this is again a question on redox reactions, but actually trying to integrate inorganic chemistry. So as you often see, I always like to classify my reactions by always looking at what I'm getting, because this helps me to reason through. Now let's have a look, guys. Why would this metal react with hydrogen chloride? And we can see here what is at play is hydrogen ions. Now if you look at our table, now it served its purpose for what we were doing. Now let's look at it nicely again. Can you see this is where hydrogen is? Right. So we are reducing hydrogen ions into hydrogen gas. So this is the direction we are approaching. So now if only T and Y, it means T and Y, it's any one of these. Okay, in fact, I'm doing it wrong. So remember, what can reduce hydrogen plus ions into hydrogen gas? It's any one of these metals at the bottom. So T and Y are from this group here, meaning these are strong reducing agents. So the interpretation of this is because these are strong reducing agents. Okay, we can say these are strong RAs. Okay, but now we don't know which one is stronger than the other, but we can already see this is a question on redox reactions. And obviously, guys, this is the question that would get 2 asterisks because it's too elusive. You wouldn't be too sure you are dealing with this. So you needed to understand the very first statement nicely so that you could appreciate what's going on. So you can see when I go on about this business, rambling and talking nonsense, it's not pure nonsense. It's actually heavenly nonsense. When Y is added to solutions, now listen to this. When Y is added to solutions of ions of the other metals, metal precipitates of T, V, and Z respectively are formed. So what does that mean? Meaning Y is strongest reducing agent, because this literally says it is reducing. Remember, solutions of ions of other metals, they form precipitates. That means we're reducing those ions into solids. So that means Y is essentially the strongest. As much as we know T and Y were stronger together, but Y is the strongest reducing agent because it reduces them all. Because it reduces the ions of the others. Okay, so that is Y. So Y is the strongest. Now metal Z reduces ions of V. Now remember, we saw that essentially T and Y are the stronger ones, and of the stronger ones, Y is the strongest. Now we've got metal Z, it reduces V. So this means Z is a stronger reducing agent than V. Great. Now the question says, the four metals in order of increasing ability to act as reducing agents, that is from weak to strong. Now we can see Y is the strongest, so this is the best option, and this one is already gibberish. Now we know that Y is preceded by T because they were stronger together. So this T is good. Okay, we're still okay there. And then we're told Z reduces V, meaning Z is the next guy and it cannot be V. So obviously V is the least of those ones. So the answer is option C. So again, guys, this is one of those questions that you need to be meticulous and to interpret statements properly. And as you can see, a lot of information is hidden in some background knowledge of subject matters that are involved. Okay, let's move on. Now, to protect a metal from oxidation, we are protecting a metal from oxidation. It can be connected to another metal that then acts as an anode, meaning it becomes a reducing agent. Because a reducing agent, whenever the ions that would result from oxidation of this particular metal we're trying to protect, this one will reduce them back. That means we will not corrode that metal. Now, which one of the following metals would protect tin? Sn. Usually they would not even write the formula, so you would have to know that tin is Sn from oxidation. Now remember, we have served the purpose of this one, so we want to go on. Oh, by the way, I forgot to tell you guys that even though we saw that T and Y are in this region, the other metals are in the other region because they cannot reduce hydrogen ions. This could be copper, this could be mercury, this could be silver, this could be platinum. Those are the metals that we can see above hydrogen. So remember that if one said choose any of these metals, that could be T, V, and Y, and Z, you would have to choose from those. If you say choose T and Y, it could be any one of these. So this is very nice. Again, a nice question can be constructed still from this little piece right here. So be very careful to pay attention to what I'm giving you guys, because there's a tendency for these things to be a question in the next exam, and you would be so happy because you have an advantage in there. Anyway, let's leave that. I just wanted to show you that essentially. Now let's go on. We are saying now we want to protect tin. So where is tin? Here is our tin. Now tin, we can see of this one, silver is above. Now remember, silver will actually cause tin to undergo oxidation because silver ions are stronger oxidizing agents than these tin ions. So essentially, that means tin will not be reduced by silver. So silver is the wrong guy. So it can't be silver. What about lead? Lead is also above tin. So that means the lead ions are stronger oxidizing agents than the tin ions, and that means these ones would be reduced by tin itself, and therefore tin would undergo oxidation, what exactly we don't want, so that would not work. And then what about zinc? If we look at zinc, it's below. There is zinc. Now zinc is below tin, and therefore zinc is a stronger reducing agent than tin, so it means it can reduce ions of tin back to tin, and that can protect. So zinc is the correct guy. So here obviously we hit the correct one, we are smiling, but be very careful. Now gold, which is Au, is up there. It's even a stronger oxidizing agent than the others, so this would cause a severe corrosion of tin. So the answer is, thank you very much, sir, you ain't important, or you are not going to help us. All right, so this one is a fairly straightforward question, obviously, not a big deal. Now, here 1.13 says a standard electrochemical cell. Now remember, once we say standard electrochemical cell, we mean a voltaic cell or a galvanic cell, meaning spontaneous reactions, spontaneous redox reactions. Remember, some wording means certain things in science. Now with an EMF of 1.2 volts, okay, was set up using two of the half reactions with reduction potentials listed below. Okay, we can see that usually the negative ones, they can act as reducing agents, and the positive one can act as an oxidizing agent. But be very careful, it depends on who is acting with who, but that's just the general knowledge. Now we need to pick up the right reactions that will give us that EMF. So this is a higher grade question, again, not too difficult, but one that needs a little bit of thought. Now let's see what is going to be the story here. We want 1.5. Now obviously we can see that the best one to look at is minus 1.5, because I know 5 minus 2 will give me a 2, and then 1 will give me a 1. So the 1,2 will come from these two guys. But obviously the least negative is going to be the oxidizing agent, and the more negative is going to have to be the reducing agent. So can you see, as much as these could literally be looked at as reducing agents, but when these two act together, the story can change. So be very careful. But now we know that this is from the knowledge that the E cell is equal to the E oxidizing agent minus E of the reducing agent. And if we look at this, this is going to be minus 0,3 minus into minus 1,5. And this is going to give us 1,2 volts. So this works perfectly. So again, guys, your mathematical gymnastics and knowledge is key here, because by inspection, you can easily work it out without wasting time and confirm it by just, making sure it is so. So we can clearly see here that the reducing agent is going to be R. So anything that starts with R is key, and anything that starts otherwise, it's already wrong. Okay, great. But now, what is the cell notation? How is it constructed? The cell notation is constructed such that we've got the cathode, let's just say anode, and then we've got ions of anode, or of the reducing agent, let's just say ions of reducing agent. Salt bridge, we have ions of oxidizing agent, and then we have the cathode. I'm just using this rough notation just to highlight what is going on. So we start with the anode, meaning that electrode. So this is electrode R, because we can see that this is more negative than the 0,3. And then it is followed by the ions, and then the salt bridge with the double line. Then is it S2 plus? We can see that no, it's not this guy, but it's R. So it's essentially wrong here. So this one becomes exactly wrong. So we look at this one. what follows now is P2 plus and then 2P solid. And that essentially speaks sense. So the answer here is D. Okay, so be very careful, guys. These questions can be a little bit overwhelming. But understanding the construct of things is key. Okay, let's finish up, guys. Which of the following compounds has the formula like this? Obviously, guys, once we see this carbon, hydrogen, and oxygen, we are probably looking at with two oxygens. This is either a carboxylic acid or its functional isomer, an ester. So it's any one of the two. So ethanol, no. Methyl ethanoate, this is an ester, but methyl ethanoate, there's already one carbon plus 2, so this should be 3C. Now, this one is basically C2, so this won't work. Ethanoic acid, yes, it's a 2C. Butanol, it's already 4C, so this one would not work, even if we were to look at it any other way. So this is already wrong, so fairly straightforward. So can you see, some questions are picking your brain for some time, and when you get used to it, then they relieve the pressure, right? Now, which one of the following will not decolorize bromine solution through an addition reaction? Obviously, these are unsaturated hydrocarbons, ethene and ethine, and this is an unsaturated rather a haloalkene. So this one will definitely decolorize this solution in an addition reaction. So if it will do it, we're not going to accept it. But what will not do it in an addition reaction is ethane. Why? Because this one will undergo a substitution. It can do it, but in a substitution reaction. Remember, when we want to form haloalkanes, we use this. In the presence of UV light, it separates these into its halide ions, and it can strip the hydrogen off the ethane, and then there will be a substitution because of the electronegativities involved, and as a result we end up with a haloalkane, and that bromine water solution will decolorize, okay, but through a substitution, not an addition reaction. So guys, be very careful. Certain questions are technical in nature. Of course, if we didn't make any silly mistakes, we could have gone home with those fat 60 marks. And you can see maybe 1, 2, three, 4, only 4 questions out of 15, guys, were simply straightforward and direct, provided you knew enough. The rest were a bit technical, can you see? But again, you will appreciate, guys, that as much as we struggled through these things, when we go to the longer questions, you will appreciate how useful starting with MCQs is as a guide of more questions in the similar topics, because these guys are trying by all means to assist you to pass, so that if you already did well in MCQs, you're more likely to even do better in the longer questions. And sometimes some areas can remind you of certain questions you could not decide on, and go back and rectify those. Or some others provide you an understanding of the others so that you just cruise with them. So spending some time with MCQs is not a bad idea, and in fact MCQs are best done first, because you don't want your brain confused and you're trying to deal with those tricky questions. You'd rather appreciate the tricks and see which ones you cannot answer immediately, but already you know where the trick is lying or where your fears are. But if you start these when you're already chasing time, you will die a slow death. Okay, be very careful. Okay, let's have a look at these questions. Okay, let me just make myself some tea quickly. Whew. Okay, guys, I'm back. Let's carry on. Now we answer these 2 to 9, in the answer book. Obviously, these MCQs have a special paper, but I'm not interested in that. So we start each new question on a new page. Instructions, guys, are to be paid attention to. Leave a line, one line between sub-questions. For example, sub-questions of 2.1 and 2.2. Now, the most important, give all formulae used and show your workings. Okay, this includes substitutions because this is how we score marks. And then we number our answers in the same way that the questions are numbered. Very important. Okay, let's have a look at what is going on here. 2.1 says, consider the boiling points, okay, of the following organic compounds. Can you see we're dealing with physical properties? Physical properties of organic molecules or compounds with their respective molar masses. So this is basically how does the molar mass affect a boiling point, literally. So again, with higher grade, guys, it was more important to look at the question given so that one can make the correct determination of how to respond to the questions. Now we can see here methanol CH3OH with a molar mass of 32 grams per mole and a boiling point of 65 degrees Celsius. Ethanol is slightly longer chain with a higher molecular mass than the previous one, has a higher boiling point, sensibly so, chain length or molecular mass, but mainly we'll just use molar masses because of what we are given. Dimethyl ether has the same molecular mass as this one. Okay, all right, okay. So, but we can see the boiling point is negative. So why is that? It already tells us that the intermolecular forces here are weaker than those of ethanol, which is similar to it. Great. So now that we understand our table, we can go on and start answering. So we've got 2.1. So with 2.1.1 says, what evidence is there in the table indicating that the intermolecular forces between molecules of methanol are weaker than the molecules between ethanol? It's basically the boiling point. So the evidence is that the boiling point of ethanol is higher than that of methanol. Okay, so the issue here is the difference in the boiling point. So someone can just say the difference in the boiling points. But again, I always like to be specific, in my answering. So that is easy, 2 marks there. Not a big deal. So 2.1.2, what does it say? Give a reason why the intermolecular forces between the molecules of methanol are weaker than those of ethanol. Okay, so what is the reason for this? Obviously, we need to use what we were given. We can see that the molar mass is less. So if the molar mass is less, but again, why? We know that these molecules are polar, right? They have hydrogen bonds, similar in number and in strength. But the difference is the van der Waals forces that are acting over a larger surface area provided by the difference in the molar masses. So this one needs us to really explain a little bit more. But we can see the real difference is the van der Waals forces, or the weak van der Waals forces, or the London forces, because they each have hydrogen bondings of the same order and strength, in fact even number. So the chain length or the molecular weight is responsible for the stronger. Now if I was to make an analogy here, let's say these molecules are the same, and then we link them with just one string, and then we take the same molecules that we have there, but now we link them with perhaps 3 of these strings. Now this one would snap easily, but this one will take effort to snap. Okay, you know that. So this would mean these ones are acting over a larger surface area than these ones, which are acting at only those little small points. So this is just the analogy that one can put in mind to try and understand this situation. So how do we explain this? We can say methanol has weaker London forces between its molecules compared to ethanol due to a smaller molecular weight than maybe let's leave it due to a smaller molecular weight. Okay, methanol has weaker London forces between its molecules compared to ethanol due to a smaller, or maybe let's say due to its smaller molecular weight, which provides a smaller surface area for the action of these forces. Because remember, it's the weak London forces that are responsible. It's not the hydrogen bondings, because they each have the same strength, same number. So easy formulas. So basically mentioning these ones and mentioning the molecular weight are the key points here. The rest is history, guys. So again, there's many ways of phrasing, the English nicely, but at the end of the day, we need to give a proper answer, a comprehensive answer. So let's move on without wasting time. 2.1.3 says, give an explanation. Now an explanation, guys, it's not just a simple reason. Although I made this comprehensive, but it says why the boiling point of dimethyl ether is lower than that of ethanol. So we can say dimethyl ether has only weak London forces between its molecules compared to ethanol, which has strong hydrogen bonds bondings in addition to the London forces. So that's primarily the reason, guys. It's just the intermolecular forces, their strength. And then we can say, remember we were told to give an explanation. We can say, the next bullet here, we can say now less energy is required to separate molecules of dimethyl ether than would be for ethanol. Hence, the boiling point of dimethyl ether is lower than ethanol for the same molecular weight or mass. Okay, so guys, this is very comprehensive stuff, but obviously, folks, the most marks are here. We have to mention the strength of the intermolecular forces acting. Okay, and we can see here there's also in addition to weak London forces. Maybe let's say in addition to the weak, something didn't really work nicely here. I don't know what happened. Why did it leave that behind? Okay, so see, mentioning the forces involved, it's a mark, and the energy requirement and the amount of that is important. So obviously that would be the second mark. Remember, the conclusion is just simply tying up nicely the same thing to suggest why are we even comparing these two when we say for the same molecular mass. This is just to suggest that this is essentially a fair comparison. Okay, so you can see, guys, all of these things come from a long way back. So this was just 2 marks, but remember, when the question says provide an explanation, do so. Don't worry about marks. The marks can be given in a way that you would not understand. Sometimes this is done deliberately to give less marks for what is an explanation. And you would think, okay, all right, okay, this is easy, and then you go around saying stupid things, you will lose marks. Okay, name the intermolecular forces in dimethyl ether. Again, we have already done this here. So 2.1.4, these are the London forces. In fact, just write London forces. Sometimes these are called forces of dispersion, or sometimes they're called induced dipole induced forces. Okay, so this is just the distribution of electrons. Remember, electrons in the orbitals move around. Sometimes others are moving slower because of being tied to the nucleus, and the ones in the outer energy levels are moving faster. So they sort of catch up on one side of the molecule, such that the other side looks a bit more positive, and therefore that instantaneously causes those forces of attraction. So that's the idea of these forces. So again, the name itself is enough for our two maragas. Two maragas. Ne? Now the question says, considering the intermolecular forces, choose ethanol or dimethyl ether, the one that is more soluble in water. Can you see? We know that water is polar and ethanol is essentially polar itself, so, or slightly polar. So that is going to be more soluble than the dimethyl ether. So we know that to answer this question 2.1.5, it's going to be ethanol or ethanol. Ujwala, the wine, the vein. Okay guys, so we're just scoring this 1 mark and nothing serious. Now the question would be, this is suggesting that this could be polar, but the symmetry of this molecule prevents that from having dipole forces, but it's only going to have essentially weak van der Waals forces, because those things here cancel each other in a way. So I hope guys we're moving on smoothly, but let's not spend too much time, we'll lose it. So let's do 2.2. 2.2 says, two learners A and B investigate the relationship between temperature and pressure of an enclosed gas. Okay, great. Now the learners used different samples of sulfur dioxide gas. The key here is that they used different samples in two identical containers. Now, identical containers mean the same volume. So the volume is even given to us that it's fixed. So it's being kept constant. Now, their results A and B were plotted on the same set of axes as indicated below. So now let's first find out here by checking. This is pressure, okay? What are the units? Kilopascals, okay? So this helps, guys. Because of these old little things here, this is pressure in kilopascals. It helps to know the unit, because at times you may come across calculations, and now certain calculations need conversion, so be very careful. Now these are the results that we see. So now we can clearly see that these are straight lines passing through the origin. So what does that mean? We know that this is from the general gas equation. PV is equal to nRT. Now if we're going to look at pressure versus temperature, then it means we're going to divide by volume times T. And essentially, we'll appreciate that this is a constant, because even though we are using different samples, but for each experiment, that is a constant. And again, where does this idea come from? It comes from y equals mx plus c. Seeing that c is at the origin, so that is 0. So this implies that y is equal to mx. And the gradient is the gradient over there. Nice and easy. So again, we know that the gradient is basically nr over v, because we are changing temperature and pressure. Okay, all right, okay. So this is very important. So do you see the question in the MCQs, guys? It's back here again. So if you fluffed it, you're most likely going to fluff this one too. But this one may just remind you enough to go and sort out the first one if it became a bit challenging for you. All right, guys, so not a big deal. So if we just read on the table, this one corresponds with that. Okay. And that one corresponds with that also. All right, okay. So let's just sort it out nicely. So remember, lines that were not originally drawn, you must not make them solid lines. All right, so it says write down the mathematical relationship between P and T that can be deduced from the graph. So we've got 2.2.1. Now, what can be deduced? This is a direct proportionality. We can see pressure is directly proportional to temperature when that is a constant. So we can say pressure is directly proportional to temperature, or to the temperature. Let's just say to temperature. When the volume is kept constant, isn't it? Because obviously the main thing that we're keeping constant is the volume. Why? Because number of moles and are automatically constant. So I don't know. Let's just leave it here and not complicate it, because the idea is the direct proportionality. I don't know, guys, what would happen if you write like this. If you write the mathematical relationship in symbolic form, I don't know. So rather, do the simplest thing and then put in brackets. Then you're covering yourself with the blood of Jesus. Okay, make use of the relationship in question 2.2.1 and determine the value of the temperature X on the graph above. So greatly, this is very easy, guys. We know that this relationship is suggesting that here, if we just work on this equation a bit more to try and derive equations, these things you can do it at a go if you're confused. So now we can see if we divide by t, we can say P over T, it will be equal to nR over V, which is nothing but a constant. So this is nothing but a constant. Okay? So if this is equal to a constant, we can see that this is a constant gradient. So even if we choose the second one, we know that if this is P1 over T1, it is equal to a constant. The same will appear for P2 over T2. It should give us that same constant because these things are proportional, isn't it? Now you know. So if those two are equal to the same constant, it therefore derives the equation that P1 over T1 should be equal to P2 over T2. So this is the ultimate dude. So again, can you see a little bit more this time than it was the case? So 2.2.2. Now we need to sort this out. So we can say P1 over T1 is equal to P2 over T2, because each one of these gives us that constant. Now, do we really need to substitute or rather change this? We don't, because in here they will cancel out. So we can just write this one nicely. P1 going to be 100 kilopascals over T1. This is 298 kelvins, which is 25 degrees Celsius. This is equal to P2, which is 150 kilopascals, divided by T2, which is what we want. So we cross multiply. So this implies that X is going to be effectively 298 into 150 divided by 100. Oops, not 1,000. So do you realize that this is kilopascals, this is kilopascals, the units will cancel, and the ones that will remain is that of kelvins. Now let's do it nicely. So this is 298 into 150, all of that divided by 100. So this gives us a 447 kelvins. And remember the unit of measurement, guys. If that unit of measurement is not written correctly, a mark is lost. Remember that. Okay, so this is easy, guys, but again, a very nice question, because you wouldn't really think of it this way, would you? Anyway, doesn't matter. So the formula, nicely constructed, substitutions, nicely constructed, and the answer, nicely constructed. So Essentially, this is a 3 mark, but now what would be the extra mark? I am not too sure. I'm not too sure. But maybe we can say 2 marks for the answer. I don't know why it's 4 marks, but this is a standard 3 mark question. But let's leave that to whatever else is cooking. So 2.2.3. Now this is another typical higher grade question. Determine the mass of sulfur dioxide gas used by learner A. Okay, now what is key, guys, is this gradient between these 2 points. Because it's the same, and the gradient will give us the number of moles. And from the number of moles, we need to therefore use the molar mass to find the mass. So this is easy. But now be very careful. Kilopascals need to be converted to pascals, because once we use this equation, the general gas equation, we need to use the standard units. So this is pascals, this is kelvins, but the volume would also have to be changed to meter cubed. Okay, we can't use decimeter cubed. So very technical stuff. But first, let's deal with our gradient. But in fact, we can deal with this all at once. We can say here the gradient is equal to P2, because this is change in y, over minus P1 divided by T2 minus T1. This is just mathematics, isn't it? So now we substitute. The gradient is going to be N, number of moles, times the general gas constant over volume, which is equal to P2 minus P1 over T2 minus T1. This implies number of moles is what we want. The general gas constant is 8,31, all divided by the volume. Remember now, the volume must be in meter cubed. So this is going to be 1 over. Now, sometimes I forget this. Let me show you the quick way. We know that King Henry died a miserable death common to mankind. So 1 millimeter is 1 millimeter, but 1 centimeter is 10 millimeters. 1 decimeter is 100 millimeters, and 1 meter is 1,000 meters. So 1,000 millimeters, sorry. Okay, and this one is going to be 10 to the 4, 10 to the 5, this is 10 to the 6. Okay, so this is a very good way of remembering these things. Now, to know how to do this, we cross-read. We say 10 to the exponent 3 decimeter cubed is equal to 10 squared meters. So we write it 10 cubed decimeters is essentially equal to 10 squared meters. And then we want 1 decimeter, so we divide by 10 cubed, we divide by 10 cubed, and that takes out. So we get 1 decimeter is equal to, now that takes the cube, so we end up with 1 over 10 meters. But now we don't want a decimeter, we just want a decimeter cubed. So we cube everything. So using our exponential rules, we will see therefore that 1 dm cubed is basically 1 over 1,000 meters. Or we simply divide by 1,000. So now we know that we're going to divide by 1,000 to convert that to meters. This is going to be equal to, now kilopascals is going to be 150 times 10 to the exponent 3, because remember we multiply this by 1,000, minus 100 times 10 to the exponent 3, all divided by, the temperature is in kelvins, already cool. So T2, we got it as 447 minus 298. All right, so guys, a few little calculations will take you through if you use them well. But if you don't know what you are doing, but I will tell you, this is noteworthy. For me, guys, when I was a student, I chose to carry knowledge enough to be comfortable. I didn't want to stress myself with cramming everything. Everything gets cluttered under pressure. So to release this, I always studied what works for me nicely, because I knew that it gives me a way of working my way through, because I didn't want to carry all of this in my head. Even knowing long multiplication, long division and stuff, when you get a question that, for example, you get into an exam where you cannot use a calculator, those things become your absolution. All right, great. So let's move on, guys. Let's move on. What are we doing? We want to isolate the number of moles. So if we want to isolate the number of moles, we simply cross multiply here and divide. But maybe we can clean this up. This is 8,31 n over, maybe before we cross multiply, let's clean it up a bit, over, now this is going to be 1 times 10 to the minus 3. Okay, great. Equal to, let's put that on the calculator and sort it out. So we've got 150 times 10 to the exponent 3, not minus 3 but 3, minus 100 exponent 3 there, and then we are dividing all of this by 447 minus 298. Okay, so guys, be very careful what you get here. So I'm getting 50 scordo divided by 149. Okay, that's a bit cleaner. Then we can cross multiply and divide here. So we can say this implies that our number of moles is going to be 1 times 10 to the minus 3 into the 50 scordo. This is going to be divided by, when we divide, this will multiply that denominator. So this is going to be 8,31 into 149. Therefore, the number of moles of sulfur dioxide gas is, so what we have, we just multiply by 10 exponent 3. So we just multiply this by 1 times 10 exponent minus 3. Careful there. It gives us what it gives us, and then we divide this whole thing by the product of 8,31 times 149. It gives us what it gives us, guys. So I'm getting 2,71 times 10, maybe we can put the 0, to the exponent minus 4. This is mole. Okay, mole. Let me just double check. Sometimes these things can be a situation, believe me. 1 times 10 to the exponent minus 3 into 50,000. Okay, we divide this one by 8,31 into 149. So sometimes these calculations need to be on point. Can you see I'm getting a different answer? So this means I wrote my own things. Again, it helps when you feel like something is not adding up, please take a pause and double check. So this is effectively 0,04 mole. Okay, there was no restriction to how much we should be rounding off. We can say here then, number of moles of sulfur dioxide gas should be equal to the mass of sulfur dioxide gas divided by the molar mass of sulfur dioxide gas. This implies that 0,04 is equal to the mass of sulfur dioxide gas, which is what we want, divided by sulfur dioxide is 32 for sulfur plus 16 times 2. Okay, just show this as a nice calculation there to avoid unnecessary issues. So this would be over 1. We can cross multiply and divide. We can say, therefore, our mass of SO2 is going to be 0.04 into 64. Right. What do we get there? 0.04 into 64. That gives us a 2.56 grams. Okay, nice and easy. Nice and easy. Okay, so you can see, guys, here that, working your way through meticulously is important, and knowing relationships of things, integrating stuff is key, and also double checking, because I was getting a strange answer here and I was like thinking, doesn't sound right, but let's look at it anyway. Could have been the answer anyway, but you just make sure you do it twice if you get the feeling something is punking you. Okay, how do we deal with this, guys? So obviously, folks, this is a calculation on its own. Those conversions and the overall calculations, and essentially these ones are already there, so it's just part of the general substitution. Sorry. And this conversion was a necessity, so we've got 3 marks already in there from just the overall substitutions and the things that we need to do. And essentially this whole thing boils down to this number of moles. So we have 1, 2, 3, 4, and then we can say formula 5, and then the answer 6. But I feel like I gave too many marks, because calculating the molar mass here is also mark worthy. It's a step on its own. Hayi man, 10 wena ngathi ufuna undilinga nje. Yeni bo. Okay, it's refusing. So it's 1, 2, 3, 4. We're scoring 6 marks. Do we really? But this is mark worthy. So let's leave this general substitution, therefore it does not matter here. So the general substitution does not matter. But this is how this 6 marks could be scored, guys, nicely. So let's finish up this question. Give a possible reason why graph obtained by learner B has a smaller gradient than the graph in A. Do you see? We already spoke about it in that question right here. Let me just take you back. Sorry for the, back and forth. Already saw that the number of moles was the reason. So now, since here we spoke about a mass, because a mass translates to a number of moles, we can easily say here to 2.2.4, we can say the learner used a smaller mass. The learner B used a, not as, used a smaller mass of SO2 than learner A. So very simple there, because we can see that definitely for us to answer this question nicely, if you look in this equation, what is responsible for the gradient difference is the number of moles, because this is fixed, general gas constant. This is also fixed. The volume was fixed, So essentially what is responsible now is the number of moles, because that's the only possible reason for this. So again, same or similar question than the other one. Can you see that MCQs are an eye into, or they are an insight into the rest of the questions? Be very careful, guys. Be very careful. So we would have scored 23 marks here if we didn't fluff anything. Remember, it's easy to write nonsense because you think, well, it's all good when it's actually all bad. So this was a very cool question. I man suphakama wonke wena man people 10 ngiyangiqhela. Athi ngikhabule ndingaginyi. Kuthiwa ngikhabula lapho ungafinci. Awuthi ngikhabula amanzi amnandi. Ndizenza ixhego. Ke liqhegu ndata. Ya, ate maqhegu re a itseba nthwena. A ke re tloeleng hento ya maqhegu re tswele pele ka thuto ndata. Wa bona. Ba re ha ke shebile tlase. Ke shebile thuto ha e tlala. In fact, let me put it better. Ha ke shebile tlase. Ke shebeletse noka ya thuto ha e tlala. Ha ya tlala e ntse fela. E tletse madi a bana ba sekolo. Bana ba sekolo ba tshaba ho e palama. Ha re batla palama leng. Ha re batla palama ka di-final exams tsa November. Ba jetse papa ke Sesotho nthwena. Ha ba tsebe Sesotho bana ba loya. Re tla ba bolaya ha monate fela. Anyway, guys, that was just to take a little break. Now, let's get to this question. Sulfur dioxide gas. You see, we're still talking sulfur dioxide here. Can be prepared in the laboratory, and we did it by means of the reaction between a sulfuric acid, yes, and a metal sulfide, yes. We did this in the lab, nice and easy. Now, let's have a look here. 3.1, it says write a balanced equation. Can you see? This was always a nice question. Higher grade guys, you would be told what to use, and you know what is one of the products. Then you have to figure out the rest and balance the equation. Obviously, students who were cram successful, people who could cram successfully, they would answer these questions quickly. But people like me, we really didn't find it easy to cram. We used other means necessary. We learned how to form compounds, chemical formulae or chemical compounds of we learned how to form formulae of chemical compounds, and the rest was easy because we just manipulate the stuff. And in fact, doing so also reminds you of what you read. So obviously it's a metal sulfate. This can be sodium sulfate. Remember, sulfate ion is 2 minus, sodium is 1 plus, so we need the 2 to sort it up. So this is Na2. Remember, we don't show the charges, but they are very important. So again, guys, it said know the compound ions in terms of their net charges. So we had a table of these, so you had to learn these again because that was a step towards an important stuff. So now this is hydrogen sulfate or sulfuric acid. Now we know that we are going to produce a salt, so which is going to be Na2SO4 plus we will find our product. Maybe let's leave our product for last. Remember, this is a sulfate. It's going to form salt. Remember, this is an acid-base reaction of some sort. It's going to be a salt, water, and carbon, not carbon dioxide, but sulfur dioxide gas. So this is the idea behind all these gymnastics. So guys, knowing these things, this is similar to acids and bases, where we take a metal carbonate, we react with an acid, we form salt, water, and carbon dioxide. Now when we take a metal sulfate and react it with an acid, we'll form salt, water, and a metal sulfide. So do you see, not a metal sulfide, man, come on, sulfur dioxide gas. So can you see from O3, we end up with an SO2. All right, guys, so this is cool. So is this balanced? Look, there's 2 sodiums, 1 sulfur. Holy cross. There's a sulfate. Okay, fine. The sulfate is easy. We leave it alone. 1 sulfur. There's 1 sulfur. Now there's 3 oxygens plus 4. That's 7 oxygens. Now there's 4 oxygens plus 2. That's 6 plus 1. That's 7. There's how many hydrogens? There's 2 hydrogens. There's 2 hydrogens. So this is technically balanced. So can you see? Just by knowing what products to anticipate, you easily come up with a proper chemical equation. Obviously, if this was not balanced, then the next step was the easier one, just to play with the balancing coefficients, which is a grade 10 exercise now. But now we're doing a metric exercise of knowing how to form these. All right, guys. So there is our target. There is our target. Our target. So this is similar. This is more of an acid-base reaction, if you think about it. But we can look at it more and see if it is more than an acid-base reaction, because sometimes one can easily say, well, acid-base reaction, one can say, is it tones and tones? I mean, you can see sodium let go of this guy and took this one. So it's typically of an ion exchange reaction, or one could look at it as an acid-base reaction. So it can fit both things. So it's always important, guys, again, to classify these reactions, because if you don't classify them, they're going to work on your nerves and cause you pain. So 1 mark for the left hand side, 1 mark for the right hand side, and for the overall balancing, leaving us 3 marks. But note the type of reaction taking place, because that also helps you to form a proper chemical equation. Just from knowing the reactants, you can work out what should be the products. This would help as well to make sure you survive these questions. So let's look, at 3.2. Now it says sulfur dioxide gas. The sulfur dioxide gas prepared is now passed over a filter paper dipped in potassium permanganate solution. Now it is very important to know that this is actually purple. And the purple color is because of the permanganate ion. Okay? So the permanganate ion is purple, is purpura. Oh, in medicine you learn some terms. When something is bluish like bruises, we call it purpura. Nice words, meaning purple. Manithi ndizama ukuthetha iXitsonga, but iXitsonga is running away from me, comrades. It's embarrassing me, actually. Okay, so let's leave this one. So can you see, guys, we looked at this dichromate stuff with sulfur dioxide gas here. Now we're using another strong oxidizing agent, which is even stronger than the dichromate ion, which is the permanganate ion. So we are back at doing redox reactions, because there's the permanganate ion. Okay, there's the permanganate ion, and it's going to be dealing with our friend sulfur dioxide gas right there. So can you see, this becomes a reducing agent that is a strongest oxidizing agent. So there's going to be a redox reaction taking place here. Okay, let's have a look at the next question. It says, what color change will you observe when the gas is passed over the filter paper? Obviously, it's going to change from purple to colorless. Manganese 2+ ions, right? Because we can see that this is Mn2+ and these ones are colorless. Great stuff. So again, this was basically memory-based stuff, because if you didn't read this in your textbook or didn't do this in the lab, obviously this goes away. But what I like is that reading this is easy to forget. But if you've seen it in the lab, you definitely will not forget. Okay, so let's answer the question. So what color change? We will see that the purple permanganate ion will change to colorless manganese 2+ ions. Okay, right, this is good. Obviously, this is just the observation. Obviously, the change is because of reduction taking place. So please don't say that if you don't need to, but you can say that purple permanganate ions will be reduced to colorless manganese 2+ ions. So I mean, there's many ways of saying this, but as long as you explain the color change, you are sorted. Now the question says write the equation for the half reaction that will explain the color change. See again, standard reduction potential, guys. Now we just need to copy what it is there. So what we see here is MnO4 minus plus 8H plus 5 electrons going to Mn2 plus 4H2O. So the good thing, those ones are already balanced. So all we do is just transcribe this nicely. So this is going to be the the permanganate ion plus 8 plus hydrogen ions plus 5 electrons. So this is to show this is the reduction half reaction, but this is being asked indirectly. So this is Mn2 plus 4H2O. Now, is this balanced? It definitely is, because we've got 8 hydrogens, 4 oxygens, there's 4 oxygens, 1 manganese. So this is already balanced. And don't even do the spectator ions. Don't do it. But if you like, you can add the spectator ions. But now, what are you going to do? What must you see with the spectator ions? For example, we said potassium permanganate. If you add potassium here, this is just going to be KMnO4, because K is 1 plus. Right. And then we say H, don'ts, and then plus 5 electrons. Obviously, we can leave the electrons. And we come here. Manganese is 2 plus. So what must it pick? Now we have a problem. That means we need to choose an acid for these hydrogens, because the best one would be sulfuric acid or even HCl. Now from HCl, we're going to have manganese chloride, okay, potassium chloride, and manganese chloride as well, and other things. So this means we will have to acidify here. So this one gets a bit complicated. So let's just leave it to the half reaction, because this is good enough, guys. Let me not complicate it. But you can see that if you start to put the spectator ion, the hydrogen must get a spectator ion too. Could be a chloride, could be sulfate, and you name them. Could be nitrate. You just choose an acid. Okay, great. So that's easy. 2 marks there. 3.4 says, does the sulfur dioxide act as a reducing agent or an oxidizing agent when it reacts with potassium permanganate? We already know that it is going to be a reducing agent. It acts as a reducing agent. I-agente. So we know this one. So again, just 1 mark there. Nice and easy. 3.5. Can you see this mark is just coming from above, from that analysis in the MCQs? as I told you guys. All right, it says give a reason for your answer. So how do we know this acts as a reducing agent? Because, now can you see that reduction comes back? Because it caused the purple permanganate ions to be reduced to colorless Mn2 plus ions. So do you see this one was not necessary to include, therefore we can take it out and say, okay, we don't even need to mention it. If the presence of sulfur dioxide gas caused the purple permanganate ions to be reduced, mention that. So if it causes something to be reduced, it therefore becomes a reducing agent. So can you see? That's the reason for our answer. And that's done. The reason is not necessarily an explanation, so we can leave it. 3.4. Now it says write down the equation of the half reaction that sulfur dioxide undergoes in the reaction with potassium permanganate. Again, we go back to our standard reduction potentials, and then we'll see that we just copy the reaction for sulfur as it is. So, but now be careful of how you need to write it. It's going to be SO2 plus 2H2O. It goes to the sulfate ion plus 4H plus 2 electrons. Remember, the half reaction must show those 2 electrons being lost. So this is nice. We wrote it nicely. And remember, we always write the equation from the left to the right. But even though on the table we're reading it from right to left, but we write it properly. That's the key. And a single arrow there. Be very, very, very careful, guys. Anyway, let's go back and answer this nicely. I'm taking a bit of time, guys, to allow time for you to assimilate these things. Because if this is not the case, there's going to be a lot of pain for you. Plus 2 electrons. So the release of 2 electrons suggests that this is an oxidation half reaction. So we're getting 2 marks. So we're getting a mark for the overall thing, a mark for the single arrow. Very important. Okay. All of a sudden I have a 3.4. Causing my slow death. Why do I want to go to the grave early? Now we said acid rain is a result of dissolving atmospheric pollutants like sulfur dioxide gas in rain water. Again, do you see our analysis in question 1? Now it says write down a balanced equation to show how sulfur dioxide reacts with water. This is the basis of our fountain experiment. Okay, so we know that this is sulfur dioxide gas plus the water bus. It gives us sulfurous acid. So this one is balanced, no stories. So can you see, guys, you're getting easy marks now. So the mark for the left, for the right, and the arrow. In fact, not necessarily the arrow, but the overall balanced equation. So without any further mistakes, guys, that we may have committed, we could have taken those marks. But be on the lookout for any errors and shout as loud as you can to make me aware so that I do not leave you confused or given the wrong information. So now, do you guys appreciate my rant that essentially MCQs are the door to the longer questions? Can you see our analysis there has saved us the day more than once in the longer questions? You know, in more than one question even. So don't look down on MCQs. They are carefully constructed, guys, to summarize the questions you are going to get in the rest of the paper. I say this all the time, but you guys don't listen. Anyway, let me drink from my fountain of life. Oh, let me drink from the fountain of life. Ndibosa ngabom. Okay, ngingacimba ndiyabosa andibozi. All right, guys, let me just sip a bit. All right. Okay, guys, let's carry on to the next question. Oops, it's one of those. Okay, now this one, guys, gave me a few issues when I was a student because I remember this one clearly. But again, my problem came here mainly because, the rest was easy to figure out. But this one gave me a bit of a situation, and you will see why. So questions like this, again, they need the doctor's approach, well applied, no nonsense. Okay, let's go on, guys. Let's not talk. We need to answer as many questions as we can in this time we have. I told you to consider the following flow diagram that represents an important industrial process. Can you see a lot of inorganic chemistry here? This process consists of several steps and we can see them. Okay, now we need to work through this nicely. Now we can see nitrogen with hydrogen and then it's forming gas A. We already know that gas A should be ammonia. Now what is this step one essentially? Step one is going to be hydrogen gas plus nitrogen gas going forward, going backward, because we know that the Haber process is reversible to form NH3. So gas A is literally NH3. So this is what we have, guys. Great. So this is the gas that we can see here. It's NH3, which is the result of step one. But is this balanced? The answer is not exactly. Can you see we have 3 hydrogens? We've got 2. So obviously, when we start to balance, we don't consider 1. So to balance, we can try 1. No, we cannot use 1. It's not useful. We can try 2, 3, 4, 5, and so forth. So always alternate from odd to even so that you can work it nicely. So let's try a 2. If we put a 2 here, it's going to be 2 hydrogens, then there's 3 there. It's not really working. 4. So this is not really giving us the vibes. It has to be multiples of 3. So that would mean, let's put a 3 in there rather. So again, guys, sometimes it doesn't work out the first attempt. So if we put a 3 here, maybe let's put a solid 3. Now this is going to be 6. So this is 3, then this should be 2. And we see there's 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. So this is balanced. So again, guys, the art of balancing is very important. Okay, so that's the equation. Can you see these were not given balanced, just to give you a challenge. Okay, gas A is reacted with oxygen to form step 2. Okay, now step 2, this is basically ammonia plus oxygen, going to give us what? If we react ammonia with oxygen, this should give us nitrogen monoxide gas plus what is going to be the other one. So remember, if we're going to form nitrogen monoxide, there's already nitrogen, so now we're left with hydrogen and oxygen. So what does that leave us? Most likely, guys, we are going to form, what is this one? The most likely one is going to be water, right? That should be the most likely thing. Okay, great. Okay, so now is it balanced? Let's play with the numbers. Same principle. We've got nitrogen here, 1, 1, so that's okay. Hydrogen's 3, there's 2, so it's already not working out. So obviously, guys, this is going to be a bit hectic. Now let's see, let's try a 2. So if we've got a 2 here, there's 6 hydrogens. Then now to get 6, we need to put a 3 there. There's 2 nitrogens, there's 1, so we put 2 there. Then oxygens, they are 2, but now we end up with 2 plus 3, that's 5. So this is already saying things that are not very nice, you know. So now to get 5 here, we need to do what? And say, maybe, let's see. Yeah, but now we need to multiply this further, because can you see? We have 5. This one is just 2, and this is an odd number. So 2 is not really doing the things. Guys, in questions like this, you need to take a bit of time, unfortunately. So let's try a 3, just following our systematic approach. So if we're saying 3 here, then we're going to have to put a 3 there. All right. Right. Hydrogens are now 9. So now this is already an odd number, so this is not going to work out nicely. So 3 is kicking us in the face. Now this is when you don't remember, but if you remember this, you will know. If we put a 4 here, then there's going to be a 4 there. And this is now 12, then that should be 6. So 4 nitrogens, 4 nitrogens, 12 hydrogens, 12 hydrogens. Now this is 2 oxygens. Now this is 10 oxygens, because this is 6 plus 2. Now for it to be 10, this has to be a 5. So that looks balanced. Now let's write it properly now, with the proper coefficients. So this is a, I went a mention papela, 4. This is going to be 5O2. This is 4. This becomes 6. So this is now balanced. Okay. So again, guys, please take time to do these. It's necessary to master this. You will know why. Why I cried for this question. It has something to do with these dudes, and you will know in just a while. So basically, gas B is literally nitrogen monoxide gas. Okay, that is the sole purpose of this situation. So it's nitrogen monoxide. There, the sole gas that we're trying to get is ammonia gas. Forget the balancing coefficients, they don't really matter. So knowing how to write proper chemical equations, guys, is very important. Okay, now let's move on. Now we take this nitrogen monoxide, we react it with oxygen, it gives us nitrogen dioxide gas. But again, we need to write a proper equation for this. Sorry, so we have here nitrogen monoxide gas plus oxygen. So this one gives us something. And in fact, let me think. I think this step 2 here is catalyzed. I'm not sure. Is this the one that's catalyzed, Ganen? No, it's not this one. Yeah, ammonia with oxygen is catalyzed. It's catalyzed. And the thing there is platinum as a catalyst, okay? Yeah, I think so. But please verify this in case I am lying to you. So this is a catalytic oxidation of ammonia to form nitrogen monoxide. And obviously here, the target is nitrogen dioxide gas. Right, that's the main target. So is that all? The answer is yes, because if we look at this, there shouldn't be anything extra. So now we just need to balance things. Now let's play again our nice game. So this is NOO2. So basically there's one N, but oxygens are 3, there are 2 here. So we need to play a very smart game. So we need something that is going to be a multiple with 2 that will balance this nicely. So we start with a 2 as usual. So this is a 2 times 2. So we have a 2 there. And we will have essentially 4 oxygens. Now they are 4. So that looks right. So this is already sorted. So let's write it nicely now. So this is basically 2NO2 plus O2 going to form 2NO2. Okay, now that 2 is trying to mess with me. Okay, so that's it. So it looks balanced nicely. So guys, unfortunately, these little pieces of work can be quite a hectic scenario, I promise you. So essentially, this one was already volunteered, so they helped us out a bit. They kind of volunteered the guess to make sure we get the right thing. Otherwise, they knew we could easily lose our way. See, sometimes they relieve the pressure there. But what do we know? Nitrogen dioxide gas is soluble in water. So this forms step 4, and this is going to form our acid. So our acid came from nitrogen dioxide gas plus water to form nitric acid plus, this is organic part A. Now let's look at this and see what is possible. So we took hydrogen. In fact, we literally took a hydroxide ion here, didn't we? We took a hydroxide ion here and added it there nicely, so that formed us HNO3, and then there's a hydrogen that's just floating in there somewhere. So the question is it floating or is it not floating? But let's just assume we need to balance the hydrogens and say, let's put a 2 in there before we run into problems. So if we put a 2 there, there's 2 nicely. Oxygens, there's 1 plus 1, that's 3, and then here we've got 6. So we have a bit of a situation. Nitrogen is 1, and then now all of a sudden we've got 2, so we need to put a 2 there. Now if you put a 2 there, what happens? It causes us problems, eh? So this is a bit of a situation. But again, guys, memory can help you a bit. But I want to show you something, guys. Now we see that, okay, now we have a situation where we've got 4 oxygens, here we've got 6. So that means we need to know what this one is. Obviously, from memory sometimes, this is what eventually kicked in my mind, that we also produce nitrogen monoxide. So nitrogen monoxide is produced in 2 separate steps here. So until I got here, I kind of struggled a bit here. Obviously, that was when I was trying to answer 4.7. Now, this is more like it. Now, let's see if it's going to be easy to balance. Again, you will see that if you forget, the most important part of the thing is we run into issues. So the idea was to form nitric acid, and that is acid C. And nitrogen monoxide, that would be compound X. And this nitrogen monoxide is the one that we will take back to this step right there. And then the vicious cycle continues. Okay, so now that is nice. So knowing the products, as I said, is very important because sometimes we cannot make them up from this easily. Now we can try to balance this. Now we've got how many nitrogens? There's 2 of them. Now we've got 2 here. Hydrogens, we've got 2. Now we don't have 2, so we need to put a 2 there. So now we end up with more nitrogens now because we've got 2 nitrogens, but now all of a sudden, okay, we've got 2 nitrogens, but plus 1, that's a 3. So that is not working. So they are off balance. Oxygens, there's 4 plus 1, that's 5, that's 6 plus 1, that's 7. So it's already giving us a kick in the face. So, okay, now let's try one more. Maybe let's leave a space here so that we can write nicely. So guys, you can see a lot of time is getting lost in here. But remember, we can recover this time by answering every question faster. Because if we're getting stuck with the questions, we will lose our way. Now let's see. We tried 2, it didn't work. Let's try 3. So you can put a 3 in there and see what happens. Now if we put a 3, there's 3 nitrogens, there's 2 nitrogens, there's 1 nitrogen, there's 1 nitrogen, there's 2 hydrogens. We can just put a 2 in there, see what happens. If we put a 2, now what happens? We've got 3 nitrogens and 1 extra nitrogen, so they are 3. So that looks all right. 2 hydrogens, there's 2 hydrogens. Now oxygens, 3 times 2, that's 6 plus 1, 7. That's 3 times 2, that's 6 plus 1, 7. So this is balanced. So you see, guys, it takes a moment, honestly speaking. But again, you will see and appreciate the fact that knowing what are the products of each particular reaction is a little bit more important, because you could see we were probably going to struggle a long time ago. I mean, I also struggled and almost gave up here, but I knew this is nitric acid, but I couldn't figure out this is, and I couldn't figure out a proper equation until this guy came back to memory. So this is one of the guys that caused me trouble. But you see, Moss, when you are a fighter, things will come back to you somehow. And obviously you can appreciate the necessity to know these things in detail, even if you don't, but knowing how to work things out, having certain comforts is also good. But again, you can see those comforts alone don't really do it the whole thing. So we can also appreciate that our acid here, we can appreciate that our acid C is nothing but nitric acid. Okay, so we can see that things are just moving nicely. So having taken a moment to analyze, now let's see if we can rush through these questions. We are told here to write down the balanced equation for the reaction taking place in step 1. This one was easy, obviously. So this is 3H2 plus N2. Obviously, guys, here we don't really care much about the reversibility or irreversibility. So we can see that we know that the Haber process is reversible usually. It uses chemical equilibrium, or it applies chemical equilibrium. So 3 marks, the left hand side, the right hand side, then overall balancing. Standard 3 marks for a balanced chemical equation. Now, how is the N2 required for this process obtained? This is from what we call fractional distillation of air. Because we know that nitrogen is found in the air. But now, because everything is mixed together, we need to know, because of its density to other gases like oxygen and you name them, if we do a fractional distillation, we know that certain areas will contain most of the nitrogen, and then we take it from there, we extract it from there. So this is the principle behind this. So you see, an easy 2 marks. Again, this one was not far-fetched. Anyone who went through this would know this. It could even come back even if you were trying to forget it. Now, step 2 is the process known as the catalytic oxidation of ammonia, and we know it is catalyzed by platinum. Now, what is the meaning of catalytic oxidation? So basically, it's a reaction with oxygen gas. Maybe let's write properly. Oxygen gas in the presence of a suitable catalyst. It has to be suitable, because not just any catalyst. It has to be the suitable and the appropriate catalyst for the reaction, because this reaction would not even occur if you put a negative catalyst, for example, rather than a positive. But key also is a reaction with oxygen, because in literal means, in principle, when we say oxidation, we mean a reaction with oxygen. When we say hydrolysis, it's a reaction with water. But we can talk about other technical factors, because oxidation can be looked at as a loss of electrons. But you will see also why these things are literally oxidation and reduction reactions. We're going to get to it shortly. So 4.3. Let us see. It says name the gas B formed in this process. So we already identified it's nitrogen monoxide gas, but now the question is name. Nitrogen monoxide gas. Okay, that is easy. 2 marks again. Can you see, guys? We are cruising. I mean, you could have answered these questions without even going through this thing. All right, write down the balanced equation for the formation of acid C. Can you see this one right here? The one that gave me goosebumps. Was almost trying to take marks away from me. And obviously I tried to skip this question for a bit, but then came back when I remembered what I needed to remember. So this is 4.4. See, the numbering sometimes can overwhelm. Be very careful, because a wrong numbering, even with the right answers, gets you no marks. Write down a balanced equation for the formation of acid C. Now there it is. So we just copy and paste. Can you see how sweet this becomes when you do our groundwork without panicking over questions? Because the problem with this, if you start looking at the questions before you analyzed this properly, this will cause you to choke to death, believe me, because you will not survive this. Once you've answered certain questions and then you get stuck, then you lose your way completely. But if you start finding your way, then these ones become a lot easier to handle. Even if you cannot answer this question, but you don't panic anymore, because knowing a bit takes away the panicking. It takes away the panicking. So let's finish up this thing. 4.6, it says both step 1 and step 3 are executed at high pressures. Now, application of Le Chatelier's principle. Give 2 reasons why high pressures are used for these reactions. Obviously, we don't know if reaction 3, step 3 here, is reversible. I'm not too sure, but I'd leave it as that. But I know for sure that one is reversible. But now let's try to find reasons. High pressure. Can you see here? There's 3 gas molecules of hydrogen gas, 1 gas molecule of nitrogen gas, totaling 4 gas molecules against 2. So high pressure will favor the reaction with the least number of moles of gas. So we will favor the forward reaction. So we want to favor the forward reaction. Same story here. There's 2 plus 1, that's 3 against 2. So we want to favor the forward reaction. So it says 2 reasons. 1, we want to favor the forward reaction as an increase in pressure will favor the reaction with the least number of moles. Essentially, we're trying to do a faster reaction rate. Okay, number 1. Number 2, obviously if we favor, it means that reaction is going to occur much faster in a reversible reaction, or essentially. Obviously, guys, I mean, increase in pressure affects the reaction rate. So we want to also increase the speed of formation of the products. So we want to increase the rate of formation of products. Okay? As, again, increased pressure will lead two gas particles of reactants being more closer together, being being more close together, leading to effective collisions per unit volume. So guys, sometimes when I cannot put a valid explanation, at times I realize that I can just manufacture some comprehensive reasons just to make sure that even if someone felt I was talking gibberish, can feel sorry for me and give me my marks. So do the same. Sometimes you need to be creative, guys, to survive an onslaught by the examiners. They can take you down. So obviously, guys, we favor the forward reaction because it results in the least number of moles. So that is Le Chatelier's principle, essentially, using chemical equilibrium principles. Now also reaction rates, because we know that we'll have more effective collisions when the reactant particles are closer together. The two gas particles, maybe let me write this one better so that you can see. Gas lead to gas particles. Qalile. Kanti theni nango? Gas particles of reactants. Yeah, this one is terrible. Okay? Being more close together. Again, you would probably wonder, what is that word? More close together. Yes, this thing is horrible, is it not? Close together, leading to effective collisions per unit volume. I believe that's the one. But obviously, guys, you see 4 marks. It's not a walk in the park. So for me, we're favoring the forward reaction is a mark on its own, and talking about the least number of moles sounds correct to me. And here we want to increase the rate of the formation of products, obviously, because these ones will lead to effective collisions when they are closer together. So for me, any one of those keywords, any 4 of them would give us those 4 marks, because you can clearly see the marks are starting to suggest that we need to be a bit more careful on how we're answering. But we may be wrong, we may be right, who cares? If we put up a good fight, who would take you down completely? Sorry, no one would. So this is my understanding of what is going on here, because yeah, remember, we want this to happen faster, because I mean, this is the industry, guys. We're using energy to do this. So now we don't want to end up losing money and using more energy. So we want to get our products quicker, because even the containers, by being too hot for too long, because I mean, this is at high temperatures and high pressures. So this would already tell you that we can end up with explosions or, you know, disasters occurring. So we want to minimize problems but maximize on profit. That's the idea here, because this is industrial work. Okay, now let's get to the one that was almost killing me. But you see, I fought even for 3 marks, guys. This was just 3 marks, but I knew I'm not leaving it behind. So let's look at this 4.7.1. We are told, does a redox reaction, can you see, I already told you from the first question already. Let me just take you back just to emphasize this point. We knew that these processes, Haber, Contact, Ostwald, you know, electrolysis of brine involved some redox reactions, and we needed to understand the, assigning oxidation numbers, which, did I even explain here? I doubt if I did, but yeah, as we went along, or as we go along, we will highlight that fact. I don't think I did, but I did here. See, this assigning of oxidation numbers is going to come into effect right here. But not just alone with these chemical equations, because what was giving me a heartache here was knowing those balanced chemical equations. This is why this is a higher grade with an asterisk. Yes, it's just 3 marks to save a student who could easily go into a serious problem here. But essentially, those were key, guys. Those were key. Now, step 1. Let's have a look at step 1. Let's assign some oxidation numbers now. Now, step 1, we see hydrogen is in its natural state. That's an oxidation number of 0. Nitrogen is in its natural state, so that is the oxidation number of 0. But hydrogen, we know that always carries a plus. Now, nitrogen can carry a plus or a minus depending on whom it is associated with. But here it definitely carries a minus this time because hydrogen carries a plus. So we always need the negative charges here doing their thing. But now how much minus? Now this is 3 plus times 2, that is 6 plus. Now this needs to be 6 plus. This needs to be 3 minus. Okay? So I'm sorry guys, now this thing is getting messed up. So that's a 3 minus for nitrogen. Now can you see? 3 minus times 2, 6 minus. 3 plus times 2, that's 6 plus. So can you see nitrogen went from 0 to 3 minus. That's a decrease in oxidation number. So that is reduction. Hydrogen went from a 0 to a plus. So that's an increase in oxidation number. So that's oxidation. Can you see? Definitely step 1 is a redox reaction. So it's a hell yeah. 4.7.2. Although this is just 1 mark, it's a situation that could horrify you. So these are some of the questions when you realize they can give you a heartache. You can be like, 3 marks, guys, come on, let me move on. But if you're like me, you'll be like, no ways, man. What if I don't go any further? Let me do it. Let me do it. So these are redox reactions at some point. Some are ion exchange, as you saw, like this one right here. Okay? So stuff like that, guys, is doing its own things. Anyway, let's have a look. Step 3. Now, step 3, this is this one right here, which produces nitrogen dioxide gas. Again, let's have a look. Oxygen in its natural state is 0, oxidation number. Now, oxygen in this reaction is 2 minus, okay? Now, this is 2 minus times 2, that's 4 minus, times 2, that's 8 minus. Now, this one needs to be a 4 plus. Can you see nitrogen has changed now to a 4 plus? Because it's capable of multiple oxidation states. So can we see nitrogen here? What is it? With oxygen, which is a 2 minus. Now 2 minus times 2, that's a 4 minus. Now we need a 4 plus. So this is a 2 plus. Because 2 plus times 2 is going to give us a 2 plus. So can you see? Again, capable of multiple oxidation numbers. But if we look at this nicely, we'll see that nitrogen went from 2 plus to a 4 plus. That's an increase in the oxidation state. And oxygen went from 0 here. Don't worry about this one. It's sort of like a spectator right now. But we focus on this. This is 0 to 2 minus, so it dropped. That is a reduction. Can you see? Oxidation reactions are literally redox reactions if you think about it. So this is a definite yes. 4.7.3. The last one. Step 4. This is this big one right here. Now, what is it? Is it a redox reaction? So let's have a look. We have nitrogen dioxide gas, water. Can you see? This is just compounds. Now, we can look at it and see what is going on here. Oxygen is always a 2 minus. Nitrogen here, but now remember this 2 minus times 2, that's 4 minus times 3, that's 12 minus. Now we need a 12 minus. Remember here, nitrogen, in this case, can be a 4 plus. Because 4 times 3, that's a 12 plus. So that balances out nicely. Hydrogen is always a plus. Okay, let's write it on top. And then oxygen is always a 2 minus. And that's nice and balanced. Now here oxygen is always a 2 minus. 2 minus times 3, that's 6 minus, times 2, that's 12 minus. We already have a 2 plus from the hydrogen here, so we need 10. So this nitrogen here must be a 5 plus, because we know it's an element of group 5. Naturally it should carry a 5 plus when it is positive. So again, this emphasizes the fact that nitrogen carries multiple oxidation states. This is because of isotopes, isn't it? Yes. So can you see the study of grade 10, isotopes and stuff, comes back here. So here, guys, what are we going to say? Nitrogen monoxide, oxygen is always 2 minus. Nitrogen here, to balance this, it has to be a 2 plus, okay, essentially. That's what it is. So this is a different isotope again, or combinations. So here, guys, you can see up. So this reaction is not cool. Okay, guys. So this reaction, guys, is not cool. And essentially, we cannot really classify this one as a redox reaction, because apha nguquphuquphu nje kuyatshintsha nje awusoze wazi uzokhetha eyiphi uyeke eyiphi. So for me, it's not. I would just say a hell no. Okay, because obviously you can see we cannot really make an informed decision of what is going on there in terms of being a redox reaction. At least we're being given a direction. Otherwise, if they said classify this without telling us in what regard, it would become a bit of a situation, don't you think? So basically, guys, we're scoring our marks nicely, but I'm not too sure about this one. Be very careful, but I'm quite convinced it is so. So we're getting 1 mark each. Okay, so guys, if nothing was wrong, this was a rather hectic 19 marks, don't you think? Of course, maybe not entirely, but the last parts are a bit situational. Yeah, but I'm sure, guys, you can appreciate the importance of knowing how to form balanced chemical equations, because it would be difficult to actually come to this conclusion right here. It would be literally difficult. Maybe the others could be easy because they're not too complicated, but this one doesn't look like we can classify it according to what we know. We really cannot. But all we can appreciate is that we took the hydroxide ion and added it there. So we can easily say it's an ion exchange of some sort. Perhaps, you know. But yeah, it's a bit technical in a way. All right, guys. I hope you are enjoying and you can learn as much as there is to learn. So can you see the integration of, tricks and techniques, and understanding what is in front of you, and also reading so that your knowledge is solid, guys. You need to reach a state of comfort in these things. Anyway, let's race through the remainder of these questions, guys, before we take too long. So we've got question 5. Okay. I'll just khabule phakancini. Awase yabanda naleti. Seyibanda nce. Sengumtsonso. All right, guys. So we are told a series of experiments is carried out to compare reactions of zinc foil, zinc powder, and copper powder, and essentially a mixture of zinc powder and copper pieces with dilute, let's choose a different color, with dilute sulfuric acid of a known concentration. Okay, so again, guys, we know that when we take a metal and react it with sulfuric acid, what is the main reaction taking place here? Let's take zinc. Zinc plus H2SO4 will yield a zinc salt, zinc sulfate plus H2O. Is it? Wait a minute. No, it's hydrogen gas. So this is it. So that's it. Now, let's see. Zinc takes the ion, becomes zinc sulfate salt, and then the hydrogen is left alone, and that's what it is. So hydrogen here is 1 plus, the sulfate ion is 2 minus, so everything is nicely balanced. Zinc is a solid here, so it's in a natural state, 0. Here it's a 2 plus with a 2 minus of the sulfate ion. This is a 0. So you can appreciate, guys, that we've got a redox reaction here taking place, considering zinc with sulfuric acid. But the question is, can copper react with sulfuric acid? That's a bit of a situation. But at times, don't bother yourself with something that is complicated. It will reveal itself. Now, the pieces are of the same size, so not a problem. So that's a controlled variable, right? Because this is an experiment. Now, we're told you, if a reaction occurs, hydrogen gas was produced, and we can see how it is. Okay, now the diagram shows the test tubes some time after the metals had been added to the acid. Okay, now we'll see that there is a reaction because there is the gas bubbles of hydrogen gas. But here they are more aggressive, meaning the reaction rate is much faster than there. Why? Because this is solid, this is powder. More surface area, less surface area of exposure to the molecules of the acid. Here, nothing is happening, so meaning there's no reaction here. Again, we're seeing that these are redox reactions, but if you look at this one, let's just look at the standard electrode potentials quickly. Now we have served this purpose, we can leave it. Now if you look here, where is copper? There is copper, 2 plus usually. And sulfuric acid. Now, what is active in sulfuric acid, guys? Because for us to get hydrogen gas, it means hydrogen is the one. So can you see this is inverted? Because copper is supposed to be the reducing agent, the hydrogen plus ions are supposed to be the oxidizing agent. But because this is inverted, it becomes non-spontaneous. So this means it does not occur if we don't put heat. So this one would need heat before a redox reaction can occur. So this explains why. Because now we understand what is the target. So again, guys, knowing the target is also key in understanding how to analyze a particular question properly. Otherwise, here we've got zinc with with sulfuric acid in the presence of copper. Now this is more aggressive, more bubbles than that. So this means copper will act as a catalyst. So that means it increases the reaction rate. This is why it's more aggressive, more gas bubbles over a short period of time than here and than there. And the reason why this is not occurring is because it's a reverse redox reaction. So this is non-spontaneous. So it would not occur without a little bit of extra heat. So this is endothermic, while the others are exothermic, because the spontaneous ones are exothermic. So we can easily say delta H here is less than 0 there. But in here, it's because the delta H is greater than 0. So that's another reason one can finish for that observation. Okay, let's talk less and solve more. Now the question says, okay, in one of the test tubes, no reaction is observed. Refer to the relative strength of oxidizing agents and reducing agents to explain the reason for the observation. Obviously, the reaction is not occurring in C because naturally copper is a weak reducing agent, whereas hydrogen ions are also weak oxidizing agents. So when weak meets weak, there's no reaction that takes place because it has to be a strong versus strong, right? So the moment one is weak compared to the other and vice versa, there's no reaction that takes place. So to answer 5, we will put out a very strong argument that 5.1.1, we can say here Cu, solid, is a weak reducing agent, as well as the hydrogen plus ions are a weak oxidizing agent, and so the reaction is therefore non-spontaneous. So you can use words to impress, guys. So this is very, very, very important. For me, this is 4 marks. I'm not too sure exactly how this is going to work, but for me, is non-spontaneous, needing energy. I don't know, guys. If it is non-spontaneous, therefore, we can simply say the reaction would need external source of energy to occur. Because we're looking at 4 marks, we just want to say as much as possible. Now, saying copper solid is a weak reducing agent, that should be a mark. Also, saying this hydrogen ions are a weak oxidizing agent, that's another mark indeed. Saying the reaction would be non-spontaneous, it would be a mark. The need of an external source of energy would also be another mark. So this is how I would think of those 4 marks, And that's how I would explain, because remember, an explanation needs to be comprehensive. Anyway, let's leave it at that in case we end up messing it up. So give a reason for the difference. Now, just a reason is not a big deal. For the difference between the rate of reaction in test tube A and the rate of reaction in test tube B. This is the surface area of the zinc. So we can say zinc powder in test tube B, provides a greater surface area of exposure to the H2SO4 molecules for effective collisions to occur. Then zinc, what is this? Zinc foil, a solid. Okay, hence the reaction, rate is faster in B than A. Okay, again, guys, this was just 2 marks. So basically, greater surface area, maybe let's write it better. For more effective collisions. So more effective collisions is a key word. The greater surface area is a key word. Now the conclusion is just, to sum it up nicely. But 2 marks here is in the bag, guys. So always try to be as strategic as you can be when faced with these questions. Let's answer the next question. Give a reason. Give a reason for the difference between the rate of reaction in test tube B and the rate of the reaction in test tube D. Nice. We can say here, we can just say Cu, solid, acts as a catalyst in test tube D, leading to a faster reaction rate than in B. Okay, the issue here is that this is a catalyst, so that's easy, 2 marks. Again, let's not even talk too much here. We could say a lot, but we just want to provide a reason. This time I think we are safe here, just saying it and moving on. So 5.2 says, consider the following chemical equilibrium that exists. So chemical equilibrium that exists in a closed container. So 4 carbon atoms or whatever plus 5 hydrogen molecules, giving us this one. Now this one is 4H10, so this is an alkane, which is nothing but butane. But this could also be methyl. This could also be 2-methyl propane. But remember, the 2 is optional. It's not really a necessity, because there's only one position a methyl group can be added to a propane. It's in the second carbon. All right, so this is following the formula CnH2n plus 2, because 4 times 2 is 8 plus 2 is 10. So again, guys, it helps to, analyze things and know possibilities, because you never know what are the next questions that can be popped. Now the equilibrium constant for this reaction at 2 different temperatures is given below. Okay, at 400, it's 10 to the minus 3. Okay, that's small, that's less than 1. So that means this results in a lower yield. Now a lower yield means less products than reactants, and simply means that the reverse reaction is more favored here than the forward. Okay, all right, okay. But now as we increase the temperature, we even get a much lower yield, because 10 to the minus 9 is less than 10 to the minus 3. So if we increase temperature, we're getting an even lower yield, meaning we're favoring the reverse reaction more by increasing the temperature. So it means the reverse is endothermic and the forward is exothermic. Great. So this is very important, guys. So always analyze things and you will understand why. Great. So the reason, it's because Kc is the products, concentration of the products over the concentration of reactants. Okay. Now for this to decrease, it means this is increasing while that is decreasing. So if we increase the denominator with a decrease in the numerator, the ratio becomes smaller, and vice versa. So this is this understanding that the yield is affected by, or can be explained by, the Kc value. If Kc value is less than 1, that's a low yield, meaning we are favoring the reverse reaction naturally than the forward reaction. Okay, let's move, guys. We don't want to waste time. So we have 5.2.1. Is delta H, heat of the reaction, positive? Now remember, this is always given for the forward. Reaction, unless stated. I'll say this as often as I can so that it gets into you. So when we are being asked the heat of the reaction, it's mainly for the forward reaction. And we can see we have discovered that the forward reaction is literally exothermic. And an exothermic reaction has a delta H that is less than 0 or negative. An endothermic reaction has a delta H that is more than 0 or positive. So the answer is, it is negative. So we write the answer. We will say negative. Okay? Great stuff. And that's it. We're just getting 1 mark. Okay? Nice. 5.2.2 says explain how we arrived at the answer. Again, 4 marks. Can you see we need to provide a comprehensive explanation? Okay, so we'll start by saying, well, an increase in temperature, we can say an increase in temperature resulted in a lower yield of products as evidenced by an even lower Kc value than initially. Already the initial one was already suggesting as much, but we didn't know which reaction is which anyway. So we can see that an increase in temperature resulted in a lower yield. So again, an increase in temperature, that's the disturbance. It affected the yield of products. Okay? As evidenced by a even lower Kc value than initially. Okay? Great. Now, what does this lead us to believe in? This is suggesting that the reverse reaction, is therefore favored. Okay? Now, favoring the reverse reaction, we can say the reverse reaction is favored. Okay, maybe let's try and put a comprehensive argument. Is favored as well as endothermic. Right, from Le Chatelier's principle, because we know an increase in temperature favors the endothermic reaction. We can say hence the forward reaction will be exothermic, meaning delta H is less than 0. Here we can say delta H for this one would be greater than 0. All right, so that's easy, guys. This is how we got to it. So obviously, explaining that this leads to a lower yield, evidenced by the Kc value, and saying that the reverse reaction was favored. That's another mark there. And stating that it is endothermic, it's a good mark. And stating the last one, that's good as well. So, folks, please make sure you always state the disturbance and use Le Chatelier's principle when we have a chemical equilibrium situation to then navigate through this. So we could score these 4 marks nicely. But some people could put 4 bullets nicely, but sometimes I like to integrate things so that I don't end up writing disconnected and cryptic things here. Remember, these things must be cohesive to one another. So 5.2.3. What does it say? The pressure in the container is increased by decreasing the volume. What effect will this have on the equilibrium constant? So we know that the equilibrium constant is only affected by temperature only. So it will just remain the same, guys. So we know that the Kc value will remain the same. So we just write as we are directed, stays same. So please don't create your own wording. We are directed to choose either decreases, increases, or stays the same, and write it as indicated, because again, you get 1 mark for the right answer and you get a 2nd mark for adhering to instructions. Remember, this is a question of whether are you a law-abiding citizen. This was an easy 15 marks. Any student could eat this one up. Perhaps a more higher grade questions, maybe 1 and 2, a bit more higher grade essentially. The others, a standard grade person could answer them easily. Okay, perhaps this one would also fit a higher grade, but I would not really believe that even a standard grade person could see that. All right, enough guys of the nonsense. This bar is crazy. I can't even read it. Yo. All right guys, so I'm a bit tired. Let me just drink from my fountain of life. Okay guys, we need to take less time now, yeah? I'm taking too long now. I am taking too long. Okay, that's a new page, so we can start another question. Obviously guys, follow instructions, start on a new page, but I'm trying to save a bit of space now. Don't want this document to be too long. Okay, let's move on. Next question, 6. We're told exactly 12 moles of sulfur trioxide gas. Can you see? Stuff that we already have been speaking about is sealed in an empty container of 2 decimeter cubed. The following reaction reaches equilibrium at 700 kelvins after 8 minutes. So this means this graph is relevant, because if we draw here a line going there, slanted. Now that one is correct, because this other bastard was just trying to bugger me. Okay, let's have a look here. What is this? Let's translate rate. Okay. Let's check this one. Rate of reaction. Okay. Great. Now, the reaction rate, so this is basically the reaction rate. Now, the units are not provided, so we don't worry about it. So it's very important to know what is on the y-axis, because it can hurt if no one knows. All right, there is the equation, nicely balanced. Now we are asked a question. If the reaction mixture contains 0.5 moles of oxygen gas at equilibrium, calculate the concentration of each species. So this is an easy question. So I felt this question was made too easy, because I mean the usual question would be this one, and then you'd combine these marks to 6 or even 7 or even 8, okay, or even 10. So, but here they became a bit silly, but I mean it's the same thing if you ask me. So 6.1, we have 2, maybe let's leave that, 6.1.1, we've got 2 SO3 going forward, going backward to 2 SO2 plus O2. Now remember, these are gases, so sometimes the state of division in a chemical equilibrium is important because it has implications. Now obviously we know that initial number of moles, then we can say change number of moles. This could be used or produced. This is now equilibrium, number of moles, and this is the concentration at equilibrium. Of course, this square bracket already says mole per decimeter cubed, so leave that. Now we started with 12 moles of sulfur trioxide gas. So initially we've got 12. Now there would be nothing. And then we are told at equilibrium we've got 5 moles of oxygen gas. So at equilibrium we've got 5. Now if we've got 5 from 0, it means we produced 5. Then 5 reacts with 2. So it's going to be 5 times 2, that's a 10. And this is 2 is to 2, so that's going to be a 10. Easy. Then here we take the difference, that gives us 2 moles at equilibrium. Now the concentration is going to be 2 over the molar volume, which is 2. That's the one. So this is going to be 10 over 2. This is going to be 5 over 2. And obviously this one would give us a 1 mole per decimeter cubed. Please write the units. This would give us a 5 mole per decimeter cubed. Sometimes I just write my own things here. And then this would be equal to yikes. So this would be 2,5 mole per decimeter cubed. So guys, these are the answers for each species. Please underline them to show that these are the answers. Okay, but also make sure you draw columns so that these can be nicely separated, because sometimes the answers can be confusing as to where they belong. See, when they are flying like this, in my situation, it can lead to some serious confusions. So perhaps it's safer to separate these things so that no one starts asking, what are you doing? You are doing this one. You are doing this one. So, I mean, guys, this is the steps that we follow regularly. So, obviously, so if we changed by 10, obviously we must have 10 at equilibrium. Forgot there. So this was 3 marks, guys. So this, guys, and remember, the units in the final answers must be stated correctly. If not, a mark is lost. I cannot overly emphasize that. So 6.1.2 says calculate the value of the equilibrium constant. So we know that Kc is going to be the concentration of sulfur dioxide gas. The coefficient becomes the exponent multiplied by the concentration of oxygen. It's always products over reactants, sulfur trioxide squared. This implies that our Kc is going to be, substitute sulfur dioxide gas, it's 1. No, okay. Sulfur dioxide gas is 5 squared into 2,5 divided by 1 squared. Please substitute properly. Therefore, Kc is, now this is the ratio of 5 squared into 2,5 divided by 1 squared. So what is our answer there? It's 62,5. Now remember, Kc is a ratio, so the molar units disappear, and that leaves us a ratio. So this is a quotient, essentially. So guys, this is a high yield. It's way greater than 1. So this is a high yield. Okay. Of course, you don't write this one, but I'm just giving it to you. So meaning this reaction is more inclined in the forward direction than the reverse, basically. Basically, this is suggesting that the concentrations of the products put together will be greater than the concentrations of the reactants put together. You see? You see? You see? Yes. This one is the formula, substitutions, answers. Easy 3 marks. And this could have been a single question. Okay, let's leave it at that. Now, guys, I asked a question that the temperature is increased to 800 kelvins at the 16th minute, and we can appreciate this is what is happening right here. Sunpapela wena ntontonzi tsa hao ke tse kae monna ke tse ngata wa tseba monna hore mathaka a rata tse ngata. That's why I'm pizza ka tse ngata le ska re ke buile dintho tse de busula mona monna ke a bua ntho tse mpe monna ntshwareleng wa tseba ke rata ho bua haholo kampa thata. Okay, guys, no nonsense. So what do we see here? Obviously, guys, the reaction that starts off nicely from the top already, that should be the forward reaction, right? And the one that picks up from 0 as the other one drops is the reverse reaction. So please, guys, don't cram the part that says the reverse reaction is usually shown with the dotted line and the forward reaction with a solid line, or vice versa. Please look at the stuff given and make a conclusion. Now we can see that obviously as the reactant particles get used up, the forward reaction will drop to that level, while this one picks up to that level, isn't it? As products have formed. And this goes on, but now at the 16th minute, we will see that the forward reaction is favored. Forward reaction is favored, and the reverse reaction basically just plays catch up. It catches up again in a new equilibrium. Okay, so we know that in here, this is the state of dynamic equilibrium. And this is again a new state of dynamic equilibrium. All right. Now, guys, please understand these things, study them well so that you can make a reason. So we are saying the forward reaction here was favored. Maybe let's write this one. The forward reaction is favored. Literally favored. Here, the reverse reaction is playing catch up. So it's catching up. Okay, great. Now we understand what's cooking here. But what could be responsible for the forward reaction being favored? This could be an addition of more sulfur trioxide gas, because we can see the yield is much higher. Or maybe we're not sure about the yield, but the reaction rate is higher. So if the reaction rate is much higher, that means we may have added more of these. Or we may have influenced the temperature, because depending on the heat of this reaction, which we don't know at this point and we cannot guess it, so we leave it at that. Okay, great. But some people who know these reactions from memory in the sulfur trioxide, sulfur, let's say in the contact process thing is, if one knows exactly how this works, you can cram what is going on, but sometimes refrain from that. They can actually give an equation that you know what this is in the textbook, but then change it around just to test your knowledge. So be very careful. Don't overly exert your knowledge onto things. Now it says the graph below shows the changes in the rate of the reaction over 24 minutes from the time that the 12 moles were put as introduced into the container. Okay, this is still speaking the same language. Now the question says, write down the balanced equation for the reaction that is represented by the broken line. This is the reverse reaction, right? Because it's starting from 0 and catching up. So it's most likely the reverse reaction. So this is now 6.2. Okay, so this is 6.2. So this is the reverse reaction. Now the reverse reaction will start from this side and go to the other side, but we write it properly. So this is 2SO2 plus O2. Now remember to use a single arrow because this is in one direction. This gives us 3SO3. Okay, don't worry about the state of division, it's not important. So the 2 marks basically is the entire equation and using a single arrow. If you use a double arrow, you are dead. But maybe you could, because you wrote this in the direction of the reverse reaction, so maybe you could be forgiven. But hey, be very careful. Half reactions are very important to make sure you don't mess up. Okay guys, easy marks, easy marks. So I forgot to highlight those marks right there. Okay, so 6.3 says this one was supposed to be the 3, they drifted a bit. What is the reason for the decrease in the reaction rate represented by the solid line between T0 and T8? Obviously this is the molecules of the reactants are being used up. So we can just say the reactant molecules are being used up, leading to less effective collisions per unit volume, and essentially a decreasing reaction rate. Hence, a decreasing reaction rate. Nice and easy, guys. But remember, the conclusion is just to wrap it up, guys. Always complete your statements and mean what you say. But the most important is that the reactant molecules are being used up. That's the most important. So this is where the 2 marks, but one can easily distribute that. If they're being used up, then we'll have less effective collisions per unit volume. And that would be the second mark. So it depends on how one wants to look at it. But the fact of the matter is the question is answered. Now let's answer some more. This must be 6.4. Okay. 6.4 says, how does the Kc value at the 24th minute compare to the Kc value at the 12th minute? Okay, now let's answer this one here. 6.4. Now let's have a look at this one. Kc value at the 24th minute right there compared to the one at the 12th minute, which is at that equilibrium. Now remember, guys, this is a higher reaction rate for the forward reaction, and we favored the forward reaction. So if we favored the forward reaction, that means our Kc value, remember this is product, just say prod over reactants. Now if we favored the forward reaction, that means the products will increase, right? Because we can see the forward reaction was favored, then it played catch up. So obviously this is at a higher state now. So that means more products formed than they were here. Irrespective of whether we don't see that, we can picture it. Sorry. And the reactants, of course, they formed again. But all we know is that the products are much greater than the reactants, essentially. So this would mean Kc should increase because Kc is directly proportional to the concentrations of products. But directly proportional to the reciprocal of the concentrations of the reactants, or inversely proportional to the reactants. So guys, mathematical relationships have been the pap and place here. So we expect a larger Kc value, at least, because we could even see that this has a higher yield, so it's going to be greater than 62.5. So here, no explanation, luckily, so we just choose larger. So this one is good, is nice. Okay, guys, so nicely so understanding what happened could give us an indication of the yield. The yield is going to be higher if we favored the forward reaction, because this was already having a higher yield here. So it definitely will be higher because we increased the rate from what it was here to an even higher rate there. Okay, nice questions, guys. Nice questions. 6.5. What is the stories? And remember. What did we know? The temperature was increased. So if the temperature was increased, again, this is suggesting now delta H for this reaction is greater than 0, meaning the forward reaction is endothermic. Why? Because we were told temperature was increased from the 16th minute. So an increase in temperature favors an endothermic reaction. So already this explains the situation, and definitely case is supposed to change. So we are happy with our decision that definitely cases should change. It can't stay the same, and it cannot be smaller. Sorry, because there should be a higher yield. All right, okay, all right. So what is the story, guys? The story is the story. Are we done? No. It says now, what does, this was meant to be 6.5, this one drifted. What does the horizontal part of the graph between the 20th minute and the dons indicate about the reaction? We can say the reaction has reached a new state of dynamic equilibrium. Okay, so literally this means the reaction has reached a new state. The most important is that this is new, because we're coming from yet another state of old equilibrium. So obviously, guys, this is worth 2 marks, nice and easy. So obviously, if we did not create any problems for ourselves here, here izenze lo mathanda hayi wena man, this thing hayi isifuna ukungilinga kakhulu. Okay, isazama ukunilinga njalo, masishiye iphambene injalo. All right, folks, let's move on. So yeah, we're taking too long now. I don't like it. Let's get to this question 7. The famous question 7. Hey, do you want to start it on a new? We don't want to waste space. But be careful in the exam. You must do as you are told. Start a new question on a new page. But I'm not going to do it because now I'm trying to cut the corners. Now, 7.1, with the 7.1.1, it says, write down the meaning of the term diprotic acid. So this is an acid that can donate 2 protons. Okay, or you can write H plus ions. Nice and easy. So very concise, no business going around the bush here. Now we're told the formula of a diprotic acid. So this is N. So the best here is H2SO4. And we've been talking about it. And remember, the question said formula, not name. So if you write sulfuric acid, you get 0. Okay. 7.2 says, now magnesium hydroxide is often used as medicine to relieve an upset stomach. The pH of the HCl in the person's stomach is 1. Okay, now it says calculate the concentration of the hydrochloric acid in the person's stomach. Concentration of HCl. Okay, nice. So this is 7.2.1. Now, we know that literally pH is defined as the minus log of the concentration of the hydrogen plus ions. Now, this implies that literally 10 to the exponent minus pH, or maybe let's just write it nicely and say this implies that the concentration of the hydrogen plus ions is going to be 10 to the minus the pH as the exponent. So this implies the concentration of the hydrogen plus ions is going to be 10 to the exponent minus 1, because we're told the pH is 1, which we can say now, therefore, the concentration of the hydrogen ions is going to be 10 to the minus 1 is basically 0.1 mole per decimeter cubed. Now from here, we know that since HCl dissociates or ionizes into 1 mole of hydrogen plus ions plus 1 mole of chloride ions, we can say therefore the concentration of HCl is going to be equal to the concentration. Maybe let's say it implies that the concentration is going to be equal to the concentration of the hydrogen plus ions. Therefore, the concentration of HCl is going to be 0.1 mole per decimeter cubed. So guys, know how to answer in an orderly fashion so that you look smart, even if you're not. Okay, thank you very much, comrades. So formula is always important, guys. And of course, one can think about manipulations or substitutions. It's really not a big deal. Substitutions, guys. Great. So the answer is here, because remember the other one was a means to an end. So you can't mark this one twice. So this one was a means to an end. So our main issue was this one. So this is where we get our 3 marks. So usually this would be 4 marks in your standard examinations. Denza ntoni nangoku? Yabona sendiyabhidizela, sendilambile futhi. Kilambile bana. Ite yami iphelile nayo. Yo. Ndifuna uyofudumeza inyama. Bendenze inyama eyosiwe. I prepared some dry flies, so now am I going to eat that one and be merry. Okay, now let's answer some next questions. So we've got a 7.2.2 says will the pH will the pH in the stomach increase, decrease, or stay the same after taking a dose of magnesium hydroxide? What do you know, guys? We know that this pH is 1. But when we take HCl and we react it with magnesium hydroxide, we know this is a strong base against a strong acid. So we're going to form a salt, which is magnesium chloride plus water. The sun. Ay man, sengqhela wena man. Wayinmarka ngoku ndiqhela kabi. So H2O, and remember guys, this is neutral, it's a salt. This one is going to be neutral, it's water. So this is a complete neutralization. But remember, from 1 to that of water, it's an increase, because the pH here ranged from 1 to 7. So that's an increase. So the answer is increases. So we will just write as directed, increase. Nice and easy. Easy 2 marks there. Ne? 7.2.3 says, a person takes a dose of magnesium hydroxide, write a balanced equation for the reaction that takes place in the stomach. We've already done it. Can you see? Papa wait was 7. So we can write 2HCl plus MgOH2 must give us MgCl2 plus H2O. Is it H2O? Is it 2H2O? There's more hydrogens. There's 4 of them. So it has to be 2H2O. Okay, a little bit of a miss up there. Okay, great stuff. So please be very careful of balancing stuff. Some things look nice, but they're actually ridiculous. So don't cut the corners. This is nice 3 marks, guys. Left hand side, right hand side, and the overall balancing. You know, my standard stuff. Can you see? We are chowing 3, 5, 8, 9, 11 out of 21. So we are even above 50%. Even if we botch this one, we can do without it. We can do without this beast right here, because this one is a kicker. Suplex City. I just sneezed, huh? I'm naughty. I can't be a teacher that is naughty, man. It's dangerous. Teachers must be, maintain law and order. Otherwise, our students are going to deteriorate, and we don't want them to deteriorate. Okay, guys, a textbook states that calcium sulfate is slightly soluble in water. And it's a precipitate, in cases you didn't know. Now, 2 learners decided to test the Derm water from a local municipality for calcium sulfate. They took a 0.5 decimeter cubed sample. So this is the volume. Nice and easy. Of the Derm water, and treated it with sodium carbonate. Now, to precipitate the calcium ions present. So can you see? There's a lot of things happening here. According to the following equation. So this is the one. Of course, they kind of volunteered this one. Because, we've been writing balanced chemical equations. We need a break. So this is good. Now, this is balanced, obviously. Calcium is 1. There's 1 calcium, sulfate ion, and then the carbonate ion. Everything is sorted. Now, what do we know? We know that also the precipitate. Remember what precipitate? Calcium carbonate. The precipitate then is dissolved in 30 centimeter cubed of a 0.1 mole decimeter cubed hydrochloric acid. Same pH or concentration as what we calculated above, which converts the precipitate to aqueous calcium chloride. Can you see? When we want to deal with the precipitate, we can acidify the solution. Now you understand what I was talking about above. Can you see, guys, how nice this thing is? Man, if you don't already enjoy this, I don't know what you can enjoy in life. Those other things are depressing, believe me. Okay, converts the precipitate to aqueous calcium chloride, water and carbon dioxide. You already know, most when you take a metal carbonate, you react it with acid, you get a salt, chloride, water and carbon dioxide. Again, similar to the sulfides. Remember the sulfides? And ndifundisa isikolo bantram. Yabona ngo ndifundisa isikolo straight and to zebia. Ndifundisa nyani ngo. Noba ningathini. Ayo question and answer session. This one is a serious revision teaching session. And guys, I'm using this to make sure you prepare for your finals in a smarter way, just to show you some varieties of how these questions can come. Otherwise, for your standard, normal, predictable exams, there's more than enough full papers that have covered for that particular situation. So look through them. Don't get tired of them, because you will be surprised when you look at a video the second time, you realize you're learning more than you actually did the first time. believe me. Okay, let's have a look at this. Calcium carbonate with hydrochloric acid gives us the calcium chloride, carbon dioxide, and water. So again, the equation is given to us nicely. Okay, one calcium, two chlorides, one carbonate, which breaks down into carbon dioxide and that oxygen there. So the oxygens there are 3, 2 plus 1, 3. Carbon is one carbon. So this thing is balanced, man. Two hydrogens. So this thing is like super duper nice. It's not hiding. Now the HCl was in excess. Uzamokuhlemakhamba ngoku. Yabona ke? Into egezayo ngezi questions guys zithetha into ende engapheli efana nam othetha into ende engenasiphelo. Sometimes ecaphukisayo ngoba abanye abantu banenhliziyo ezincinci bayakhawatheka. Now this means guys, it says funeka ube nengqondo. Ingqondo. Now guys, ingqondo means insight in English. So if you don't have insight into this topic, izakubulala. Ingqondo doesn't mean brain, guys. Be careful. People need to know the right Xhosa language. Ne? Ingqondo doesn't mean brain. If brain ngesiXhosa sithi bubuchopho. Okay? Ubuchopho. Yeah. But xa sithi ingqondo, it means ukuqonda. Insight. You see, uqonda, it's a deeper understanding that is even more user-friendly. Hey guys, andazi ngayichaza kanjani. Yabona ke nesilungu sivele sinyamalale, but that is the thing. If you don't have insight here, you will die because there's a lot of things. So you need to know how to select the right pieces of information for the right activity towards the right goal and achieve it at the end. Okay, so now this was in excess, and guess what? Stuff happened. This one was neutralized. It was neutralized by a 15.8 centimeter cubed of a 0.1 mole per decimeter cubed solution of sodium hydroxide. Again, they relieved us the unnecessary stress of forming that balanced chemical equation. It's nicely balanced. Now the question says, calculate the mass of calcium sulfate that was present in the dam. As you can see, this one is suplex CT. Okay, all right. So, insight, ingqondo. And you know, someone with an insight will use the doctor's approach. Hey guys, maybe ndizocimba ndiyachoma khawuthi ndiyeke nale nto kuthetha ngale doctor's approach, because akho mntu owazi into ngobugqirha sesi-students akwa-matric. Now I was already a guy who can, look ahead. I always was the guy who knew that if I was to solve a problem in someone, I would need more knowledge. And therefore I tried to picture what could be the reasons for these issues. And science kind of, opened that thing in me. Okay, guys, sendiyalibazisa. Ngiqamela umuvelane na. Ufuna ungiqhela kabi. Awungangiqheli, andifuna ukuqhela. Okay, guys, we need to calculate the calcium sulfate. Now, using our approach, what are we going to do? Well, we know that we need to start here to find the HCl in excess, because this is the key to the log. Now, this guy is our friend. So we need to use this equation to find the excess, the number of moles of excess HCl. Because the number of moles of excess HCl and the number of moles of HCl here initially present will give us the number of moles of HCl used. Okay, so we want to know the excess number of moles of HCl so that we can picture how many did we use. Because the number of moles used, half of them are going to give us the calcium carbonate present in that precipitate. And the number of moles of calcium carbonate present is literally 1:1. So will give us the number of moles of calcium sulfate. So can you see? So if we find the number of moles of calcium carbonate, we literally have the number of moles of calcium sulfate. and we use the number of moles of calcium sulfate with its molar mass to find its mass. So this is very easy. So we start from bottom to top. So let's start here. So first of all, guys, what we're interested in is the number of moles of excess HCl. So we're going to say number of moles, not like this, of HCl excess. Okay, maybe let me write it here nicely. Oh, so libazisa when is going to be equal to the number of moles of sodium hydroxide used, because it's a 1-to-1 ratio, so we don't need to overly explain this. This implies that the number of moles of HCl excess is going to be equal to, now number of moles is going to be concentration, which is going to be 0,1 into the volume, but now the volume needs to be converted. So this is going to be 15 divided by, now we do the conversion, so it's going to be 15,8 divided by 1000. Again, if you forgot, I showed you how to use King Henry died a miserable death common to mankind. Or if you are smart enough, you can see that this is going to be 0,0158 decimeter cubed. So this is important. Now we can say, therefore, the number of moles of HCl that was in excess is the answer there. So we've got 0,1 into 0,0158. Okay, that gives us a 1,58 times 10 to the minus 3 mole. Does it ring any bells? Remember, in the table above, in one of the reactions here, we talked about these concentrations. Can you see? These guys are just playing with our heads here. But anyway, in a nice way. Okay, guys, now we have the number of moles in excess. But now our target is to find the number of moles of calcium carbonate used. So we can say here, but the number of moles of calcium carbonate. Remember, this is the 1:1, so we're going to use this one indirectly. Is going to be equal to, now remember, this one is going to be half, because this is 2, then it's going to be half from this equation. Is going to be half the number of moles of basically HCl used. Okay, be very careful. Now this is from the second reaction here, or the second equation. Okay, now what is this thing? This is just nothing but a skillful way of answering in a nice way. So this implies that the number of moles of calcium carbonate is going to be equal to, because remember HCl was in excess, so we just want the one that was used. It's going to be half of, now remember, the HCl that was used is going to be the original. The original now is 0,1. It's going to be concentration multiplied by its volume. 30 centimeter cubed on the calculator is going to be 0,03 divided by 1000. 1000 is going to be 0,03. So it's 0,03 minus the one in excess. Now the one in excess is going to be 1,58 times 10 to the minus 3. So guys, I'm trying to be as comprehensive as I can. Therefore, the number of moles of calcium carbonate here is going to be that value right there. So let's say 0,5 into 0,1 times 0,03 minus 1,58 times 10 to the exponent minus 3. So guys, be very good at these calculations, because they will give you things you will never know. So this is 7,1 times 10 to the minus 4 mole. Okay, so that's it. Let's double check again. 0.5 into 0.1 times this is 0.03. That would give us the number of moles, minus what was in excess, 1.58 times 10 to the exponent minus 3. So this one yields exactly what we have. And someone may actually choose to write the 0.0071. So that means if we move 7, we moved it 4 times. 1, 2, 3. So this is something like that, ne? Because we're going to make the 7 jump 1, 2, 3. In fact, it's on the 4th, so it's going to jump 1, 2, 3, 4 decimals. So that is what happens here. So this could be written like that, but let's leave it in the scientific notation to avoid problems. Okay, guys, I'm becoming too relaxed. Now, remember, the calcium carbonate used here is the one that was there, and it's effectively the one that's there. So we can say here safely, since the number of moles of calcium carbonate is equal to the number of moles of calcium sulfate, it therefore concludes for us that the number of moles of calcium sulfate is going to be equal to 7.1 times 10 to the minus 4 mole. Because this is a 1-to-1 ratio, man. So can you see, in this one, we didn't need to do much. We just need to say that. We can say then, number of moles of calcium sulfate should be equal to the mass of calcium sulfate. I don't know why I like carbonate. Over the molar mass of calcium sulfate. Now we do the things. So this is 7.1 times 10 to the minus 4 equals the mass of calcium sulfate, which is what we want, divided by the molar mass here. Calcium is 40 plus sulfur, this is 32, plus 16 times 4. Nice and easy. So this is over 1, and then we cross multiply the business, and what do we know? We can make a conclusion and not waste any more time. So that the mass of calcium sulfate is going to be, let's just show this one nicely, it's going to be 7.1 times 10 to the exponent minus 4 into, let's just do that calculation nicely. So 40 plus 32 plus 16 times 4, which is 64, guys. So this gives us 136. Okay, great stuff. So what is this going to be? 7.1 exponent minus 4 into 136. So this gives us a 0.097 grams. So let's just leave this one to 3 decimal places. But one could easily round off to 2 and take 1 here and add. It's going to be 0.1 grams. That's still small. But the quality of the answer speaks sense, because remember, they are giving us clues so that even if we make a mistake, but an answer should be closer to expectation. Calcium sulfate is slightly soluble in water. That means there's going to be less mass of calcium sulfate dissolved compared to the water. And we can see this one is even less than 1, guys. So definitely, if it is less than 1, it's definitely small. So the quality of the answer speaks sense in terms of the given condition. that this is grams grams, yeah man, grams, yeah. But yeah, we've done our job, guys, and our answer is convincing. The steps are quite comprehensive. Again, I'm showing you the technique of answering properly instead of pfeffering around doing long lanky things here. You must show inside, man. When I'll sing Gondo. Anyway, we're scoring 10 marks. Sorry. Now, this number of moles of sodium hydroxide is a calculation on its own. Okay, great. And this conversion to decimeter cubed from those dons. So do you realize, guys, that this volume didn't matter? In a way, we never really used it. So can you see when I talk about inside, but maybe if you did some other calculations, you may need to use it. I don't know. But in my opinion, it doesn't really seem like it's working any magics because it's not doing anything. Okay, all right, okay. But now it makes me worried if I'm not making a mistake, but I'm not. I think I've done the right thing here because that volume alone without concentration or something is really insignificant. So let's leave it alone. Unless we were told there was a relationship in terms of concentration, then we would start talking sense. But what makes me worry though is that this was an insoluble thing. But in any case, when we reacted this with this one, it took all the calcium because we wanted to precipitate all the calcium that was in the dam water, meaning the one that was soluble. So I don't think we need that one. But be very careful, eh? Be very careful. And this one, so those easy 3 marks, guys, are important. But now, what else is important? This calculation here is important on its own. And the overall substitution here, because taking half, again, it's yet another calculation complex. So we've got 5 marks here, guys. 5 marks. Maybe we can even say this one is 6. I don't know. Must be generous, but that was a means to an end. Maybe we can give this mark here because we can't mark it twice. So 1, 2, 3, 4, 5, 6. And usually formula 7. Now substitution into formula 8. And then, now this substitution carries this calculation of the molar mass. Now that one also. So we can say here this calculation literally and essentially the general substitution and the final answer. And remember, the final answer must carry this dude right there. Okay, so let's see how many marks now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course. Although, guys, there's room for mistakes in this kind of calculation. It can be a horrible situation, believe me, but it's not too bad. So knowing how to, dynamically maneuver certain steps nicely in a comprehensive way can save you time and heartache of doing too many separate calculations. Just complex things nicely, but keep track of everything. Okay, I don't know how many times I've shown you guys how to deal with these questions, so you should not be horrified when we go through these ones. Anyway, let's not waste any more time. Let's rush through question 8. Now nicely on a new page. Okay, guys, I'm hungry. I need to go eat my meat, but I want to finish this thing now nicely. Now, the following half reactions occur in a rechargeable nickel cadmium cell. Okay, fine. Now, obviously, if we can recharge, that means this thing works spontaneously. So this means this should be a voltaic cell naturally, or galvanic cell. Why? Because we can recharge and pretty much leave it to function without doing anything. So that's why we know it's spontaneous. Interesting. Cadmium hydroxide here, solid, adds 2 electrons. So this one you cannot tell which one is the anode, which one is the cathode. But what gives us the clues is the negative value against a positive value. So this would mean this must be the reducing agent, because we know reducing agents have more negative, reduction potentials compared to oxidizing agents. So again, guys, understanding things nicely is always important. So there's no manga business here. I mean, even using the standard reduction potentials here, we can even consult them. We can see that cadmium is here and nickel is up here. So the one that's above is likely to be an oxidizing agent. The one below is likely to be a reducing agent. So this is a reducing agent. This must be an oxidizing agent. But of course, the oxidizing agent must be looked at from this side, the nickel ions. Be very careful not to use this as an oxidizing agent. You will die. Okay. So we can see that, well, this speaks truth. Okay, great. So this is a spontaneous reaction, definitely a voltaic cell. Now, let's go on and answer questions at a snap. Remember, redox reactions are usually forgiving. You can answer them at a go and get stuck wherever you need to get stuck and unstuck yourself. Which electrode, cadmium, or the nickel dondons, is the anode? Remember, the anode is the reducing agent because oxidation takes place. So in which electrode? The cadmium electrode. So we will just write the symbol as directed. So this is just 1 mark. Nice and easy. 8.1.2 says write down the equation of the oxidation half reaction. Okay, now remember this is already written nicely, but now oxidation starts from right to left. Okay, that's always the case because electrons are the key to the puzzle, that we must release electrons. So when we write this, again, it's written so that you don't see it nicely, but now we're going to write it nicely. So cadmium plus this one, 2 hydroxide ions there, as it is given single arrow, guys, be careful. So this goes to CD OH2 plus 2 electrons. So don't try to mess things up. This is given nicely and it's balanced. Just do it. Just do it. Okay, so again, guys, using a single arrow is key, and the rest of the equation in the right order from right to left. That's oxidation in our table A. Remember that, or even table B for that matter. So again, easy 2 marks, guys. They were just being donated. 8.1.3 says write down the balanced equation for the reaction that takes place when the cell is in operation. Now we can see that, oh, we need to do some serious thingies here. Now you can show how you did it, or you can just write nicely, but let me just show you the entire thing. So obviously we start with the reducing agent, or whatever, the oxidation half reaction, however you want to see it. So we'll write this one, CD plus 2OH minus single arrow CdOH2 plus 2 electrons. Then the oxidizing agent here is doing its own things. Now the oxidizing agent must start with the side that has electrons. So this is nickel oxide and hydroxide also. I don't know how to read that one. This one is confusing me, guys. I'm sorry. Sometimes I'm not so clever, hey? Now this one with water. I'm not going to care about the states of division at the moment. So we go to nickel, oxygen, no. hydroxide solid there plus the OH minus ion. And then, no, this is it. Now I forgot something. I must include electrons because electrons must appear on the right. So this took 1 electron. Okay. Now guys, be meticulous. Certain equations can be made to frustrate you deliberately. So make sure you copy everything right. And obviously guys, we need to balance this beast. And how do we do this? We simply multiply this one by 2 because the key here is the number of electrons. So if there's 1, we need 2 electrons. Once you balance electrons, everything will balance automatically. But be careful, it may need one more step. But let's write this nicely now with this situation. Remember, always start with this one on the right hand side. So this is going to be CD plus 2 hydroxide ions. Plus now we take this side, eliminating the electrons. This is NiO into OH. Plus H2O, leave the electrons alone. So we're going to have CD OH2 plus, now we write this thing here, Ni OH2. Oh, no. Be very careful, guys. Now I forgot. Remember, we multiplied everything by 2, so there's going to be a coefficient of 2 here. Okay, and the water went with this one, so this one also must have a coefficient of 2. Okay, and also this one is going to be 2Ni OH2 plus 2 OH minus Okay, so again guys, what do you notice now? We've got like terms appearing the same way on either side of the equation, so those ones will take each other out. So our final and the best of all is going to be CD plus 2Ni O into OH plus 2H2O going into CD OH2 plus 2NiOH2. Yeah, that's it. Now let's see. CD1, 1 CD, Ni2, there's 2 Ni's here, oxygens, there's 2 here, right, plus another 2 here, that's going to be 4, plus another 2, 6. So now we've got 2 oxygens here, plus another 2 here. Sorry, we've got 2 there. Here we're going to have 2 times 2, that's 4. 4 plus 2, that's 6. So the oxygens balance. Hydrogens, we've got 2 plus 4, that's 6 hydrogens. Again, there's 2 here, right? Plus here, there's 2 plus 2, that's 4, so that's 6. So the hydrogens are balanced. So guys, once you get the final answer, underline the final answer because this means you are done. Okay, so guys, this was a tricky one. So obviously an answer only could work, but showing the steps is also okay. So usually you get a mark for the left hand side, you get a mark for the right hand side, and for the balancing, standard 3 marks. Or one could distribute the marks by multiplying this by 2 and then working out this step, and then the final step, that could also be 3 marks. However one looks at it, it would work. Okay, great. So this is, again, you can see this was heavy on calculating things. Oh no, son papel. This was heavy on writing those balanced chemical equations. Now calculate the EMF of the cell. This one is easy. E cell is equal to E oxidizing agent minus E potential of the reducing agent. E cell is now that of the oxidizing agent. Remember, that's the cathode. That's the one. So this is 0.54 minus into minus 0.81. Therefore, our E cell is going to be 0.54 minus into minus 0.81. So this gives us a 1.35 volts. Don't forget the unit for the final answer, guys. You lose a mark. Okay. 0.54 minus into minus 0.81. Sometimes, you know, your brain can get tired. You can lose marks easily here if you don't pay attention. So some calculations are better repeated than just assumed to be correct. Of course, correct formula. And essentially this substitution and this substitution is key to know which one is which. Right, and the final answer with the correct unit. Nice, 4 marks right there. So we've got 8.1.5. It says now, in which direction do electrons flow when the cell is being recharged? Remember, when it reaches equivalence, electrons have moved from cadmium to nickel. But now when we want to recharge, we want to reverse the situation, because this is now electrolysis or electrolytic reactions, which are non-spontaneous. Now we want to strip the electrons from nickel back to cadmium so that we can let this function again. So this is the reverse. So the reverse is going to be true. So it's going to be from nickel to cadmium. So this is the answer right there. A very interesting question. It's actually a proper higher grade question, but probably even higher, even though it's just 1 mark. To know this is very nice. So meaning when we are recharging something, we're just reversing the reaction so that we take back what was borrowed so that it can be borrowed again. Okay, so it's going to be nickel OH to CD. At least they gave us the way in which we need to answer. So that's just 1 mark. Nice and easy. 8.2 says now, chlorine gas can be prepared industrially by means of electrolysis of brine. Do you see? We spoke about it. Now make use of this table of standard reduction potentials to write down the oxidation half reaction for this preparation. Very nice. So this is 8.2.1. Obviously, with this now, we need to construct the cell. So guys, here we've constructed our cell. So what do we understand is that when we put a battery, the negative terminal will cause that plate to be negatively charged. The positive terminal will cause that plate to be positively charged. And obviously, this solution of concentrated sodium chloride is going to be sodium ions and chloride ions as well as water. Remember, water is a dipole, so it can take part in this thing. So we need to be careful. So obviously, the positive terminal here becomes the anode. Okay, and in the anode, oxidation takes place. And then the negative terminal is the cathode. It's the reverse of the voltaic cell, and here reduction takes place. Okay, great stuff. So now we know that the ions in the solution are going to move according to the electrical attraction here, electrostatics. Do you see, guys? You cannot just jump around here. Knowledge is power, folks. It is more than power itself. Okay, let's maybe choose something that we can see when we work with. Now, obviously, guys, chlorine could latch on here, right? but also water could do it. So now what's going to happen here? It's a very technical situation. Water could do that, and then sodium could do that, or water will latch onto that. Because it's a dipole, the positive end will then do it. Okay, because it's a dipole, the negative end could do it. Sodium is positive, it can do it. Chlorine is negative, it can do it. So who is who and who's going to do what? This is where the challenge is, guys. But obviously we are saying here we want to produce what? Chlorine gas. Now we know that for us to produce chlorine gas, we need to oxidize the chloride ions into chlorine. So this is already saying this is going to be 2Cl minus. So going in this direction into Cl2 plus 2 electrons. So we take it from here, guys. Not a big deal. We just take it from here, right there. And obviously we write it from right to left because that's oxidation. Now the question is, why not water? Why not water? This one is a bit tricky now, guys, because look, water, if we look at water, for example, here is water. Water is a stronger reducing agent than chloride ions. So this is most likely the one that should be oxidized. Right? Right. But now we know that in the chloralkali industry, we are trying to produce what? Hydroxide ions. So this means we're actually reducing water. So this is the one that happens. We're actually reducing water to hydrogen gas and the hydroxide ion, which we're going to use this with sodium to form sodium hydroxide. Okay, so now this one is a bit tricky because the question is, if we're using the standard reduction potentials, this is suggesting that a stronger reducing agent is water than the chloride ions. So this is where it gets a bit hottish. But now the question is, what the hell? Now obviously, guys, if you look at the concentration, remember brine is literally a concentrated solution of sodium chloride. So this is HCl. No. This is NaCl. I'm feeling a bit tired now. NaCl. That is concentrated. So does it make any sense? Yes, with concentration it means there's more chloride ions than the water molecules. Since water can take part in either, it gets confused, I would suppose, and therefore this guy becomes a clear winner. But this one is not sure whether I want to go here or go there, but because I'm outnumbered by the chloride ions, this is going to happen. Okay, so perhaps this is the story right there. All right, okay, all right. Ne? Yeah, that's the story. So I believe so, because I mean this is relatively satisfied, but this one is hungry for, you know, an electron here so that it can get reduced. Sorry, it wants to release these electrons because it's not in its natural state, so it's unstable. This one is relatively stable, so it's a bit of a tricky one. Again, this means know your textbook work. Otherwise, guys, 2 marks in the bag, no issues. Let's not talk too much. You can see there are some gray zones which are hard to explain. So maybe your teachers can explain it better, or your textbooks, or whatever resource you've got. Now it says, considering the electrochemical properties of chlorine, give a reason why chlorine gas does not appear freely in nature, but must be prepared when needed. Obviously, guys, looking here, chlorine is a very strong oxidizing agent. This one is a very strong oxidizing agent, right? So it's a very strong oxidizing agent. Now remember, there's lots of naturally occurring elements. You know, things like water water can easily do the same thing here. Water can reduce this thing back into chloride ions. So we can see that, well, because of its very strong oxidizing ability, it gets reduced by a lot of naturally occurring reducing agents, and therefore it's difficult to find it in its gaseous form. So I would use that. So again, you see the standard reduction potential, guys, needs to be understood. So you can say, since Cl2 gas is a very strong, it's not just a strong, it's a very strong oxidizing agent, and because of this story, that's why we can use it as a detergent. You see, it's there in jig. If you know what jig smells like, that's chlorine, and that could also tell you the smell of nitrogen dioxide gas. It has a choking smell, as well as sulfur dioxide gas. So take jig, that's chlorinated substance there, and we use it as a detergent because it oxidizes things. So that's how we break the stains. Because now of its very strong oxidizing, maybe we can even highlight this one, very strong, it's a very strong oxidizing agent. It will be reduced to Cl minus ions by the many, let's just say the many naturally occurring reducing agents. Maybe let's not even mention, we can say e.g. water, zinc, you name them, but essentially let's just leave it alone. As long as we know naturally occurring strong reducing agents, I think that is key. Okay, naturally strong reducing agents will literally not leave this one alone, because strong versus strong equal to a redox reaction, right? Right. So guys, I think we have done our job here. So essentially saying that it is a very strong oxidizing agent, and it will be literally reduced by strong reducing agents that are naturally occurring as well. So I would suppose this is where the 2 marks, guys. Sometimes it's not so easy to construct an argument here, but if we used the right tools to justify our position and it's fair, we should score full marks. Now, is the industrial preparation of chlorine gas an example of an exothermic reaction? We could see that it's definitely not exothermic, but endothermic. Why? Because it's non-spontaneous. And exothermic reactions are literally spontaneous reactions. So it is not. So the answer is a big no. Is it an exothermic? The answer is a hell no. Why? Because we know that an exothermic process should be spontaneous, and this one is not spontaneous. Why? Because we used a power source. So that's it, guys. So we get our last mark, and obviously we can see that these are the easy 16 marks up for grabs. But I wanted to take the liberty to explain a little bit. But yeah, perhaps the challenging one was the balancing. The rest was fairly easy. Okay, guys, now guys, let's ask ourselves, who goes in here? Because the margin here is not so much, the distance between these two is not so much. Now the concentration would play a part. obviously. But what is the distance between these two? Let's look at this one. Now there is water. Where is sodium? There is sodium. Can you see the distance is much greater than these two? This one is just one step below. But this one is how many steps below? 1, 2, 3 steps. So the distance is much greater. So this would suggest that as much as this is highly concentrated, sodium is happy actually like this. Sodium is happy shedding this extra electron because it wants to assume a stable state. So it would not be competing for electrons essentially. This one in its ionic state, it's a bit lazy. So this guy is opapa, iepa. So water would be the one that actually gets, reduced. And we know that it gets reduced to hydrogen gas. So we'll see bubbles here of hydrogen gas as well as the hydroxide ion, which will pick up this sodium. Now this one will be happy to team up with the hydroxide ion to form the sodium hydroxide, which is one of the products. So I believe that would be a better explanation, but I'm not sure, guys. If I'm talking gibberish, you judge for yourselves. Now let's end this pain. Okay, it was not a pain. Let's end this fun, Yes, it was fun. Hexane is a component of petrol, so we always talk of octane, but yeah, whatever is volunteered, we take as it is. So 9.1.1. Okay, it says now name the homologous series of compounds to which hexane belongs. Now, by its suffix, we know that this is alkanes. Alkanes. Okay, easy, 2 marks. Wow. See, sometimes the examiners can be quite generous. This was supposed to be 1 mark. Write down the balanced equation for the reaction that takes place when hexane burns in excess oxygen. So the key here is excess oxygen, meaning this is going to be a complete combustion. Now, complete combustion yields 2 things, carbon dioxide and water or water vapor. So again, knowing the products is very important, guys, because it helps us to then balance the equation. So this is going to be essentially hexane, it's C6H12 plus 2, that is going to be 14. Then we react it with oxygen, obviously. And then we want to form carbon dioxide plus water. Whether water vapor or just water, it doesn't matter. Usually water vapor. It's a gas. Now we need to play with our balancing coefficients. Now we've got 6. There's 2 here, so we can put a 6 here. Now that's fine. Hydrogens, there's 14, and there's 2 here. We can put a 7. Then the oxygens are the problem. Now we've got 6 by 2, 12 plus 7. That's what? 19. 12 plus 7 is 19. So we've got 19. It's an odd number. So an odd number provides us a bit of a problem, because now it forces us to do other things. So now we want to make 19 here. So if we want to make 19, it means we can just divide the 19 by 2. Sometimes drastic measures we can make 19 over 2. Because 19 over 2 is going to be half of 19 times 2, it gives us 19. So everything is balanced. But now this is not allowed. We can't have a fraction in terms of the molar ratio. So we will have to multiply by the common denominator. This will yield 2C6. H14 plus. Now when we multiply by this, we're just left with 1902. Then we come here, we multiply by 2. This is 12CO2 plus by 2. This one is going to be 14H2O. Now let's sort it out. Now we've got how many? 12 carbons. There's 12 carbons. 14 by 2, that's 28 hydrogens. That's 28 hydrogens. We've got 19 oxygens. In fact, 19 by 2, that's 38. Yeah, 38. Then here we've got 12 by 2, that's 24, plus 14, that's 38. So it's a definite yeah, doch. So you can show the steps as long as you underline the final answer. But if you write the answer only, it's still okay. The left-hand side, the right-hand side, the overall balance. Standard 3 marks. Can you see? Just being thrown with marks here. But one could consider how you worked it out. This is just to show, man, if you know things, okay? 19.2. It says, now the following extract appeared in an evening newspaper. Explosion rocks winery, or the winery. A huge damage occurred at the Rietboom winery. Do you know what Rietboom means? Riet means the reed. Boom means tree. So basically just the reed. So literally the reed. So Rietboom. Sometimes you can hear reed flay. That's now a reed swamp, isn't it? Because flay is a swamp where there's mushy, muddy, watery, soft ground. Umqobhozo ngesixhosa, you know, swamp umqobhozo. So siyazazi reeds, and in Xhosa, what is a reed in Xhosa? Sithi yingcongolo. So in Xhosa, the reed yingcongolo. Ezingcongolweni zifumaneka phi? Emqobhozweni. Ndikufundisa isiNgesi ne-Afrikaans nesiXhosa at the same time. Yayibona le nto? Ne-science ngaphezulu. This is called multitasking. Yeah, man. There's a little woman inside me. Yo, that's crazy. There's this man who believe there's a woman trapped inside a man's body. How ridiculous. Some people can be crazy, man. You see, freedom sometimes yields fools. Anyway, let's move. There's plenty of them. Now let's go on. It says now huge damage occurred in the Rietboom, meaning in the Riet 3 winery, a stainless steel tank in which the sparkling wine. Now why is it sparkling, guys? When we see sparkling things, we know there's a gas that is formed, CO2. Yawena. That is for the sparkling component. Is produced, exploded yesterday. Now the fermentation of sugar in the grape juice apparently took place at such high rate. See, if we're producing too much of this, the number of moles will collide with the container walls, increasing the pressure and leading to poops if the valves don't release this thing. Okay, the rate that the valves of the tank could not release the gaseous product of this reaction, and we know that this gaseous product is this friend right there, and that's the one responsible for the high pressure that led to the explosion. Can you see, guys? Inside, and it's drawn from understanding this using the doctor's approach. Now write down the formula of the product of fermentation that caused the explosion or the tank to explode. So we've got 9.2.1. We know that it's CO2 because we are asked for a chemical formula. So this is CO2. Easy. 9.2.2. Write down the name of the alcohol formed in the tank. We're trying to form ethanol. The question is name. Ethanol. So one could easily say systematic name. This is ethanol because you can't say ethanol. It's just ethanol. Some people can say acetanol, but that's a common name. It's not a systematic name. But here you can use that word acetanol. Now, when a bottle of wine is left open, now meaning open to air. And what is air? We know that there's oxygen there besides other things. It tastes sour. So why? Because oxygen reacts with the damn thing. So we know that ethanol plus oxygen will yield ethanoic acid. Guys, knowledge is power, ne? And an acid has a sour taste from acids and bases of grade 10 and grade 7, whatever. This is great, so we know what's going on. But now the question says name the chemical process. Now remember, a reaction with oxygen is oxidation. So that is what we need to write down here. So this is 9.2.3. So this is oxidation. So this is good. Easy 2 marks, guys. Not a problem. Easy 2 marks. Guys, they were just being generous. Sometimes this is bad. Is bad if there's such an English. Man, neologism is allowed because in the dictionary we can add many words as we want. Now, using structural formulae, write down the equation for the reaction that takes place between the alcohol and ethanoic acid. Can you see? Indirectly, they're just telling us things. Okay? So we know that when we react a primary alcohol and a carboxylic acid, we form an ester. So this is esterification. This is a typical higher grade question. Nice and easy. So 9.2.4. Well, we know that this is going to be ethanol. Ethanol is 2 hydrogens like this. Okay. Let's just leave some space now here. Maybe let's do 1, 2. So this is going to be hydrogen, OH, hydrogen, hydrogen, hydrogen. And remember, structural formula, guys, only apply for the organic component. The inorganic component, you don't need to show the structural formula. Okay, plus this one is also going to have OH, but we invert it. Okay, this one is going to be ethanoic acid or ethanoic acid. This is how acetic acid looks. It's CH3COOH. You know, even the molecule. Now, guys, we react this in the presence of a catalyst H2SO4. I don't know if it is necessary, and some mild heat. This is used as a catalyst so that we can use less heat here. And what is going to happen, guys? Remember, the ester or the acid can donate a proton. So protolysis is the thing here. So this is the hydrogen that gets stripped off. Okay? But we know that this primary alcohol, we know that this dude is too busy. It will shed this OH group. I know your textbooks say the hydrogen is the one that gets shed and then the OH. That's ridiculous. Because remember, this sheds this to form the alkyl group. This one sheds the hydrogen to form the ethanoate or the carboxylate ion, which will later link with that nicely to form an ester. So again, use a bit of sense, guys. Don't believe every rubbish that's written in the textbooks because it's ridiculous. There's no logic in that thought that says this is the hydrogen that goes and this is the, come on. The acid can donate a proton, not the rest. Remember that. But use your integration, guys. Acids and bases. You see, Mos. This is the story. Okay, let's do the ester now. The ester is going to start with the hydrophobic end. So the hydrophobic end, maybe let's move these guys a bit to provide us space. Now the ester will start with the hydrophobic one. It doesn't matter which one you write and how you orientate this. The hydrophobic end is the ethyl group. Now this will link to that remaining oxygen from the ethanoate ion, which links with this carbon like that, which also links with the other carbons nicely like this. Okay, now what is the inorganic product or byproduct is the waterpas, because it's the hydroxide ion plus the hydrogen will form H2O. See, this is properly balanced. And let me warn you guys, for the inorganic product, please don't waste your time showing this as a structural formula. We only use structural formulae for the organic component. So this is it, guys. This again is a typical higher grade question. So the proper structural formula for the alcohol, and for the carboxylic acid, and for the ester, and obviously the byproduct. Sorry. So this is how we score these 4 marks. Okay. Now, guys, I took longer than I wanted. I wanted to just take 3 hours and some minutes, but now I'm already taking 5 hours. Anyway, guys, this was a comprehensive review to teach you at the same time, show you the techniques. I don't think you'll ever find a video as comprehensive as this one and many others that you find in the channel. They don't exist because people are pressured with time and they forget the most important: understanding in the onlooker. They focus on impressing the brilliant students, which is bad. So sometimes people get carried away with silly things that actually make their work less effective, because if you want to make your work more effective, you need to give it time so that the onlooker wins. And in fact, most of the people, or majority of the people, have very difficulty understanding complex matters. So you need to take time to get them through. Very few are smart. So now what's the point of enhancing a life of a few against the many? You see, Mos. So guys, I'm not sure, but yay, I'm saying what I have to say, Mos. Who cares after all? Nobody does. But maybe others do. And they cry about it, which is, I am sorry. Anyway, write down the systematic. So we use this word systematic to suggest IUPAC. Sometimes you can even be asked a silly question: what is IUPAC standing for? International Union, right, of Pure and Applied Chemistry. Now let's have a look here. Write down that IUPAC name of the organic product formed in the reaction in question. Don't. So this is the ester. So the ester, we call it an alkyl alkanoate, meaning it's the alkyl group from the alcohol. Alkyl meaning it lost the hydroxide ion, and the alkanoate, it lost just the hydrogen to form a carboxylate ion, alkanoate. So we start with the name, alkyl alkanoate. The alkyl is ethyl. Then this is ethanoate. Nice. That's the right name for the things. Now, folks, we get 2 marks for this thing, because the 1 mark is for the ethanoate part and the 1 mark is for the hydrophobic end. And that gives us 2 marks, guys. And we seal the 17 marks. Okay. For a grand total of 200 marks, if we did not mess up anywhere. So guys, I hope you enjoyed the video and have learned a lot. Yes, it's a long video, but you can call it a workshop of some kind, because here we literally did the entire chemistry, guys. It's like giving you lessons from grade 10 to grade 12. So I actually combined 3 years in 5 hours. I mean, that should be something. That should be something. Obviously, we cannot explore everything there is, but we can give you as much as we can. All right. Okay. All right. So, guys, I don't know, man. I think this paper was enjoyable, at the same time a little bit challenging, and I think that's what the students who have done their work would want to see in the exam. Something challenging, but not too bad. But obviously those who don't study well, and sometimes it's not their fault because it's how they are taught, so can be unfortunately a drawback for those guys. But either way, let's not talk too much. Let's leave it here and see what happens. So guys, this memorandum is going to be published in the description together with this question paper attached here, so that you have one single document, so that you can just print it out nicely. Okay. And obviously I will remove these workings here, but you will see them in the video for reference. So I hope, guys, you're going to learn best and practice well, and of course prepare effectively. Don't chase time when you're trying to solidify your knowledge. But obviously at this point in time, you should be working towards chasing time, because you should already have a great understanding of everything. But again, it's not always the case. But sometimes a crash course like this can actually supplement what is necessary so that you can speed up. Obviously, a smart student can finish this in 2 hours, maybe some few minutes, which is what I did. And the questions that gave me a hassle, I went back to them and hustled them successfully. But of course, under the moment of pressure and anxiety to do well, some mistakes here and there do occur. Some misrepresentations of what I'm trying to say also do occur. And with less time to analyze everything. But the most important, guys, is to finish within reasonable time so that you can look back and double check some of the questions you thought were challenging to make sure if you're answering correctly, because usually the easy ones, you are more likely to answer them correctly. Okay, guys, let me live and love you. And this is probably my last video you'll ever see me post in this channel, because I'm about to go into something major, and as a result I will not have time to give you these. But guys, if you look at this, this was a paper we wrote 20 years ago, literally 20 years ago. And you can see 20 years later, most of the stuff is still being examined commonly on every single exam for the past 5 years even. So you can appreciate that this is definitely relevant, and that means the content in my channel would essentially be relevant even for the next 5 years. Okay, although there can be tweaks and changes, but I can assure you the manner in which I presented this work, I presented it such that it's relevant no matter how you look at it. Okay, guys, I hope you will do well in your exams and make us proud, make excellent professionals who will be very effective in building our nation. We depend on you folks. We're already too old, and a lot of time has elapsed with us not doing much of what we should. So we're already behind our time. So definitely die before we can achieve everything we're capable of. Hence, we are igniting you guys by providing the oxygen from our decomposition. As we age, we just spit out the oxygen for you guys to pick up and excel. All right. Goodbye, guys. I will see you when Jesus decides we should meet. But personally, I have no more time for this. But those of you who know me, and those of you who have my contact number, when you run into a problem as you practice, please don't be afraid to throw a WhatsApp message or whatever. I'll respond accordingly. But I will probably not respond in this nature. But sometimes there is some extra time, you get bored doing what you're doing, you want a break. I may throw in a video or not, but now a video is going to be like short videos usually. It's not going to be these comprehensive ones. All right, guys, enough is enough. You see, I already said goodbye. I don't know how many times, but I didn't say goodbye. Now, finally, goodbye and good luck.